Your lecturer is Professor James A. Sellers. Dr. Sellers is Professor of Mathematics and Director of Undergraduate Mathematics at the Pennsylvania State University. His engaging teaching style has earned him a wealth of honors and distinctions. These include the Mathematical Association of America's Allegheny Mountain Section Award for Distinguished Teaching and Penn State's Mary Lister McCammon Award for Distinguished Undergraduate Teaching.
Hello, and welcome to the Teaching Company's Algebra II course. My name is James Sellers, and I look forward to working with you as your Algebra II instructor throughout this course. As we begin this course together, I'd like to do a number of things. First, I'd like to introduce myself to you. I'd like to introduce you to the general topics and themes for this course. I'd like to share a number of other thoughts about things like graphing calculators and other things that will help you to work through this course. And I'd like to begin our mathematical conversation with a review of order of operations as well as laws of exponents. So let me begin by sharing a few details about me. I received my PhD from the Pennsylvania State University in 1992. While I was a student at Penn State, I met my wife, Mary. And in 1992, when I finished my PhD, I moved on to my first teaching position at Cedarville University, which is in Ohio. After 9 years at Cedarville, I went back to my alma mater, Penn State, and in 2001, I became the director of undergraduate mathematics there. My wife, Mary, and I have 5 children, one of whom is now a student at Penn State. 2 are in high school, 1 is in middle school, and 1 is finishing up her elementary school years. For a number of years, we've homeschooled our children, although several of them are now in schools, but we've really enjoyed working with them one-on-one at home as we've taught them mathematics and English and a variety of other topics. I've also spent time writing texts, especially secondary level texts, for a number of companies, the main one being Saxon Publishers several years ago. I love to teach. It's something I've enjoyed for probably more than 20 years, and I hope you'll notice by the time we've completed this course together that it's a real joy for me to teach and to work with you on this algebra material. So, what's this course about? Well, in a nutshell, this course will include a number of topics from the usual high school Algebra II course. But it's important for me to note that we can't cover all the topics that would be taught in a high school Algebra II course. After all, we've only got 18 hours of lecture time together. But I'll try to talk about a variety of very important topics that would appear in the usual Algebra II course. So here are some of the things that you and I would discuss throughout this course. I want to start with just some prerequisite basics, things like order of operations, laws of exponents, solving linear equations, principles of graphing, asking the question, what does a function look like and how do I detect one, and so on. And after we've covered these prerequisites for a few lessons, I want to move on to solving systems of linear equations and inequalities. From there, we will move on to quadratic equations and quadratic functions. And that sounds kind of big and lofty, but it's just degree 2 polynomials. And we'll spend several lessons on quadratics. It's a very, very important topic in any Algebra II course. From there, we'll talk about things known as conic sections because they're very, very closely related to quadratic equations. And conic sections are just things like parabolas and hyperbolas and circles and ellipses. After we've dealt with those quadratics for several lessons, we'll move on to polynomial equations and functions, especially as they relate to things like factoring and graphing, and even finding the zeros of a polynomial function. Now from there, we move on to other types of functions, and these can include power functions, or what we might call root functions, like the square root or the cubed root function. We'll also talk about rational functions, including how to graph rationals, how to combine them with the usual operations of addition and subtraction, multiplication and division, and we'll also talk about something really neat called composition of two functions. And we're also going to talk about one of my favorite topics in an algebra course, partial fractions, which are extremely important not only in algebra, but also in later courses, including calculus. After that, we'll talk about exponential and logarithmic functions, and then we're going to close with some of my favorite mathematics. We'll talk about combinations, permutations, and a little bit of elementary probability, because all of these things relate to something called the binomial theorem, which beautifully connects algebra to combinatorics. Now, within each of these general topics that I just shared with you, we're going to concentrate on several strands or themes. And these would include things like the following. We're going to always want to master the basics. Mathematics is a very step-by-step process, and understanding how to handle basic steps one at a time allows us to build the course beautifully, and it also allows us to master the material. So we will constantly think about how we can master the basics one step at a time. I also want us to talk about graphing a lot. Mathematics is often thought of as symbol manipulation, and I think this is unfortunate. We want to talk about being able to see the mathematics as well. And so we will talk about graphing and how to visualize graphs throughout this course. We're also going to spend a lot of time focusing on functions and defining things like domain and range and really understanding what a function is in this course. I think that's very important as we go into Algebra II. And lastly, I want to make sure that we think about the strand of critically thinking about our solutions. After one gets an answer in a math course, it's very, very important to ask, does this answer make sense? Does it really answer the question that was given to me originally? And so on. So we'll talk about critical thinking as we walk through this course together. Now, one of the most natural questions that you should be asking as we start this course together is, why is algebra important? Well, let me try to answer that in several ways. First of all, high school algebra is the prerequisite course for all other higher level math courses, including things like trigonometry, precalculus, and calculus. And to be honest with you, my hope is that this will not be your last math course, that you'll use this course as a stepping stone for future courses. So one of the reasons algebra is important is because it's a stepping stone for things like trigonometry, precalculus, and calculus. According to several studies that have been conducted in recent years, students who master Algebra I, geometry, and Algebra II are much more likely to succeed in college-level mathematics. So our algebra foundation is very, very important. But why is algebra important in its own right? Well, I could share lots of different answers with you, but let me just say this. Algebra is extremely important in a lot of problem-solving situations. Being able to go to the abstract from just basic arithmetic allows us to solve tons of real-world word problems. And without algebra, there would be no calculus. And without calculus, much of what is done in physics and engineering and related areas couldn't be done. From designing machinery to electrical circuits, none of it would be doable without calculus. So you probably have lots of questions that we should ask and try to answer before we really get into the math of this course. So let me try to ask some of those questions and to answer them as well at this time. So one question you might have is, will this course require a certain calculator? This is actually a question I get all the time at Penn State. Let me answer that question by sharing a bit of philosophy on calculators with you before I try to answer your specific question. I think calculators can be very useful, and I use one all the time. But I fear that students sometimes are allowed to rely on them too much. And because of this, I will not focus on calculator usage in this course. If you'd like to use one, especially as we try to look at the various graphs of functions that we'll see in this course, that's fine. Otherwise, you'll probably rarely use one with me in this course. So you don't need a specific calculator as we walk through this course together. Okay, another natural question to ask would be, what's the textbook for this course? Well, I can answer that one pretty easily. I don't have a particular textbook to suggest for this course. There are lots of different Algebra II texts on the market today, many of them with titles that say Algebra II. I would encourage you to supplement the work that we do in this course together with any of these Algebra II texts that are on the market. The workbook that accompanies these lectures is meant to serve as a beginning guide. If you want to supplement that workbook with a larger text in Algebra II, please feel free. Now, with that workbook in hand, you should be asking, how do I use that workbook with these videos? And that is a really good question because there are lots of different things you could do with these resources. Let me just make one suggestion. I would suggest that as you begin a new lesson, you briefly read over the material in the workbook first. Then put the workbook aside and start the lesson on the video. Once the lesson is done, and I've completed that lecture, I would then return to the workbook, reread the material a second time, and then work through the exercises that are at the end of the lesson in the workbook. It's extremely important that you do those exercises at the end of each lesson because by practicing, you're going to learn the material better, you'll master those basics that we've talked about already, and you'll be ready to move forward to the next lesson. Now, one of the best ways to learn math is by doing it. That's what I was just saying. And in this course, you'll get to try some of the problems on your own before we work through them together in the lesson. So apart from the problems in the workbook, you'll even have the opportunity during the lesson to work through some problems. And even if you make some mistakes as you're doing it, you'll learn the material faster and better if you actually work through or solve the problems than if you just sit back and listen to me and watch me do the problems. So I want to encourage you as we're working through the lesson together that you work on the problems before me and see if you get those answers even before I work through the steps. So grab a pencil, grab some paper, and be ready to stop the video when you see this certain cue on the screen. Once you think you've got the answer, start me back up, get the lesson going again, and we'll see how you did. And in some ways, you'll be able to check your answer at that point. So, with that as an introduction to this course, I'd really like us to get going with some actual math. I think we should do some math today. And so, let's get started with the topic of order of operations. So, as we work together, we're always going to have to worry about adding, subtracting, multiplying, dividing, even doing something called exponentiation, like taking 2 to the 3rd power or something like this. And it's very important that we know in which order we must complete those operations. And so we have these things called order of operation. And in today's examples, I want to focus on order of operations issues just in arithmetic. So basically adding, subtracting, multiplying, and dividing just numbers, as well as raising numbers to powers, like I said earlier, taking 2 to the 3rd power. We'll also have to deal from time to time with having mathematics inside parentheses, and we need to know when to do the work inside the parentheses versus when to do the work that's outside of those parentheses. So these concepts on order of operations will be very important not only when we're manipulating numbers, but also when algebraic expressions, variables like x and y, come into the picture. So here are a few basic ideas that we must always remember. In simplifying a complicated expression that has parentheses and exponents and additions and subtractions, multiplications and divisions, we have to do them in this order. And that's why we call it order of operations. the first thing we have to do is always work on what's inside parentheses first. If the problem has a set of parentheses in it, you must do the material inside the parentheses first. That's the wisest thing to do, and it's the correct thing to do. Secondly, as you read the problem from left to right, you must perform all of the exponentiations later. That's a big word. I simply mean perform the operations where one thing is being raised to the power of another thing. Again, like 2 to the third power equaling 8, or 3 to the fourth power equaling 81. So we've done what's inside parentheses, and we then compute all of the exponentiations. The third step in the order of operations is, again, reading from left to right, perform all of the multiplications and the divisions that we see. So if you see any numbers being multiplied by each other or divided one by the other, we need to do those next. And lastly, we want to perform all of the additions and subtractions. And again, we need to do them as we read them from left to right. So that's the set of order of operation rules, if you will. And now let's put these into practice. So to do that, I want you to try the following first on your own. Let's compute 10 plus 7 minus 5 plus 3 minus 18 plus 25. So here's the cue. Stop the video now. When you think you've got the answer, start it up again. So how do we solve this? Well, we see a mixed set of additions and subtractions. We're going to read from left to right, and we're going to work through the operations one at a time. First, we see that 10 plus 7 is 17. And then we take the 17 and subtract 5. 17 minus 5 gives me 12. 12 plus 3 is then 15. 15 minus 18 is a negative 3. And negative 3 plus 25 is equal to 22. So my final answer is 22. And now I get to ask you, did you get that answer as well? I hope you did. And if you didn't, it's okay. We're going to keep working through some more examples, so don't worry. Let's see if you can get this one. I want you to compute 7 times 4 divided by 2 times 3 divided by 6. The cue tells you to stop the video and work the problem for yourself first. You'll learn a lot more doing that. Okay, now let's solve this together and let's see how you did. Just like with addition and subtraction, problems that have a mixture of multiplications and divisions should simply be computed left to right. So let's work through this problem together. We've got 7 times 4 divided by 2 times 3 divided by 6. So the first thing I'm going to do is 7 times 4, that's 28. So now I have 28 divided by 2 times 3 divided by 6. I continue to work left to right. 28 divided by 2 is 14. So now I have 14 times 3 divided by 6. I keep working left to right. 14 times 3 is 42. And so now I'm down to just 42 divided by 6. And that one's pretty straightforward. I get 7. So hopefully you got 7 as your final answer as well. Okay, so far so good. Now let's complicate things just a bit. I gave you a few examples where we had some additions and subtractions, and then we had some multiplications and divisions. Now what I want to do is mix these up a little bit more together. So let's do the following example. I want to look at 10 divided by 2 minus 3 times 5 plus 7 times 2. Now, my question to you is, according to the order of operations, do we just start on the left and work our way over to the right side? No. You have to remember that multiplications and divisions always take priority. They always get done before additions and subtractions. So we're going to multiply and divide everything first, then we'll add and subtract. So see if you can do it now. Stop the video and see how you do. Okay, so how do we handle? Well, first we're going to work left to right doing all the multiplications and divisions. And by the way, I don't mind if a division is first and a multiplication is later. Multiplications and divisions have the same priority, so I'm just going to work my way left to right and handle all the multiplications and divisions. So the first thing I see is a 10 divided by 2. I'm going to compute that, and it's going to then give me 5. So my problem is now 5 minus 3 times 5 plus 7 times 2. Now, as I'm reading left to right, I want to skip over that subtraction and move to the multiplication that I see, because I have to do multiplications before I do any subtractions. So I'm now going to compute the 3 times 5. And when I do, that gives me 15. And so now my problem is 5 minus 15 plus 7 times 2. Now I see a subtraction, then I see an addition, and then I see a multiplication. The multiplication must be done first. And that's the 7 times 2. So I'm going to compute that and give myself 14. And now my problem is 5 minus 15 plus 14. And now notice, we've taken care of all the multiplications and the divisions, and we're down to just one subtraction and one addition. And those guys can be done just left to right, starting with the subtraction. And when I do 5 minus 15, I get negative 10. So I have negative 10 plus 14, and that's equal to 4. And that's my final answer. And if that's the answer you got, then you're doing a great job as we walk through this. And by the way, let me point out before we do the next example that we were just doing basic steps. Did you notice how we just took it one step at a time? It's extremely important as you do math, even when we get some really big looking problem, to just pause, do things one step at a time, and before you know it, you'll have the answer. It might take a moment to write it up on a piece of paper, but you'll get to the final answer as long as you follow those rules and master those basics. Now, let's do one more example of the type that we've been doing. I'd like you to try it yourself first. Here's the problem. 10 minus 5 times 8 minus 2 plus 17 minus 13 times 2. Now, let's solve this together. Well, I'm going to read left to right. I'm going to look for all of those multiplications, and if there are any divisions there, I want to do those first. Of course, first, I should have been looking for parentheses, but there aren't any. And secondly, I should have been looking for exponentiations, but there aren't any of those either. So now I need to look for multiplications and divisions. And as I read from left to right, the first one I see is 5 times 8. And 5 times 8 is 40. So my original problem is now 10 minus 40 minus 2 plus 17 minus 13 times 2. Now I start reading left to right again. I'm going to skip that subtraction. I'm going to skip another subtraction and an addition and a subtraction, and I'm going to get to a multiplication. And I see that 13 times 2 sort of dangling on the end. It has to be done first before the additions and subtractions. And 13 times 2 is 26. So now I have 10 minus 40 minus 2 plus 17 minus 26. And everything that's left is just a subtraction or an addition. So I can just march through those one at a time, starting on the left and working my way through to the right. So I have 10 minus 40, that's negative 30. Minus 2 gives me a negative 32. At that point, the problem is negative 32 plus 17 minus 26. Negative 32 plus 17 is negative 15. And when I take negative 15 minus 26, I get negative 41. And that's the final answer. Now, we've seen how to handle mixtures of additions and subtractions, some multiplication and division operations all together. But of course, I haven't thrown any exponentiation in yet, and we really haven't had any parentheses either. So let's look at an example with some exponentiation. Now, remember, exponentiation really is just repeated multiplication. So what I mean by that is that if I take 3 and raise it to the second power, 3 to the 2 is just 3 times 3, and 3 times 3 is 9. And if I take something like 2 and raise it to the fifth power, it's just 2 times 2 times 2 times 2 times 2. And if you multiply all those 2's together, you'll get 32. Remember that exponentiation is just repeated multiplication, and according to the order of operations rules, exponentiation has to be done before multiplication and division. So let's look at an example now with some exponentiation. I want us to compute 5 plus 3 times 4 raised to the second power. Okay, the first thing that we have to do is the exponentiation. Even though as you read from left to right, it's way over on the end, I still have to do exponentiations before I do multiplication or addition. So I have a 4 raised to the second power, that's 16. So my original problem is now 5 plus 3 times 16. Next, I want to do the multiplication, because multiplication takes priority over addition, and 3 times 16 is 48. So my problem now is 5 plus 48, and of course I finish by doing the addition. 5 plus 48 equals 53, and that's the final answer. And I hope that you got that even before we did it together just now. Now, there's one last thing to consider with order of operations, and that's parentheses. Anything inside parentheses always gets solved first. Remember, that was part of the order of operations rules. So I want us to try an example with just a little bit of parentheses thrown in. Here's the problem. 10 minus 5 times the quantity 8 minus 2 in parentheses plus 17 minus 13 times 2. Now first we have to simplify the 8 minus 2 that's in the parentheses and write that as 6. 8 minus 2 is 6. And now the problem becomes 10 minus 5 times 6 plus 17 minus 13 times 2. Now I don't see any exponentiations. That's what I would have to do next in my order of operations rules. So I skip to multiplications and divisions. Notice how it's just the same thing over and over. And if I do that starting from left to right, my problem is going to convert to 10 minus 30 plus 17 minus 13 times 2. And of course that 13 times 2 is 26. So now the problem is 10 minus 30 plus 17 minus 26. Well, now we're down to just additions and subtractions. So we just march through them going left to right, and we can do subtractions before additions if we need to. The point is just to do them from left to right. So 10 minus 30 is negative 20, giving me negative 20 plus 17 minus 26. And negative 20 plus 17 is negative 3. So now I have negative 3 minus 26, and when I combine those two, I get negative 29. Notice that when the same example was completed earlier in this lesson, when I didn't have parentheses, the answer was negative 41. You may or may not have noticed that I just changed those two examples a bit. Here we got negative 29 as the answer, and those parentheses make a really big difference. You always have to compute whatever's inside the parentheses first before you do anything else. Now, I'd like to talk a bit about one other important mathematical topic as we close out this lesson, and that's the concept of laws of exponents. Now, throughout this Algebra II course, we're going to need to remember these laws. They're going to show up over and over again. So let me remind you of them today, and then as we need them, we're going to use them over and over. So there are 3 laws of exponents we need to remember. First, if you have x raised to the a and you multiply that by x raised to the b, it's the same as just doing x raised to the a plus b. So the exponent becomes the sum of a and b. The second law is x to the a divided by x to the b equals x to the a minus b. And lastly, if you take x to the a and then raise that to the b, it's the same as x to the product a times b. So let's see if we can solve a few examples quickly of this type. I want us to take 2 to the 5th times 2 cubed. I want us to get 4 to the 9th divided by 4 to the 3rd. Let's also compute 3 to the 2nd divided by 3 to the 8. And then let's do 2 to the 7 and raise that to the 3rd. And lastly, I want us to compute negative 2 raised to the 3rd power and then raise that to the 4th power. Now, did you get the answers that we needed to get? Let's see. 2 to the 5th times 2 to the 3rd is 2 to the 5 plus 3, which is 2 to the 8. 4 to the 9 divided by 4 to the 3rd is 4 to the 9 minus 3, which is 4 to the 6th. If I do 3 to the 2nd divided by 3 to the 8, I get 3 to the 2 minus 8. And one way to write that, of course, is 3 to the negative 6th power. Some folks like you to rewrite that as 1 over 3 to the positive 6th power. We can talk about that some more later, but either of those answers would be fine. 2 to the 7 to the third is 2 to the 7 times 3, which is 2 to the 21. That uses the third law of exponents we saw before. And lastly, negative 2 raised to the third raised to the fourth is the same as negative 2 raised to the 3 times 4, which is negative 2 to the 12th. And since 12 is even, that's just 2 to the 12th, and the negative sign gets canceled. Well, today we've learned about the basic structure of this course. I've talked a bit about some of my philosophical views of it. And we've started our mathematical journey together with a discussion of two things: order of operations and laws of exponents. Next time, we'll continue our review by talking about solving linear equations. I'll see you then. Our goal in this lesson is to begin learning how to solve linear equations. We could say that we want to find the solutions of a given linear equation. That's the same way to say it. What do I mean to find the solution of a linear equation? Well, it's a great question, especially if we're supposed to be finding these things. So let's start with a definition for the solution of a linear equation. Basically, it's this. The solution of a linear equation is the value of the variable that makes the equation true. Let me show you a quick example of what this means. I want to start by showing that x equals negative 2 is a solution of the equation 10x minus 14 equals negative 34. Now, to show that negative 2 is a solution of this equation, we simply replace x by negative 2, or plug negative 2 in for x, and simplify to see if the equation that we get is true. So if I start with 10x minus 14 equals negative 34, I plug negative 2 in for x, and that gives me 10 times negative 2 minus 14 equals negative 34. 10 times negative 2 is negative 20, so I have negative 20 minus 14 equals negative 34, which is the same as saying negative 34 equals negative 34. And that, of course, is correct. That's true. And that means I really did have a solution. Now, I'd like us to consider how we would actually find the solutions of linear equations. I gave you the solution a few minutes ago when I told you negative 2 was a solution. We're going to try to actually find these things. And that's a tougher task than the one that I just showed you, but it's still very doable. So let's start by finding the solutions of equations which are known as one-step equations. Now, solving one-step equations is exactly what it sounds like. It's going to take one step in order to solve these. So let me show you a couple of examples. Let's first solve x minus 9 equals negative 3. Now, in order to solve this equation, we want to find a solution, which is just a number, that I'm going to plug in for x that makes the equation true. In order to do this, I want to get x by itself on the left-hand side of the equation, and I want to do that in mathematical, legal ways. So I want to be able to add or subtract or multiply or divide. I need to do something in order to get x by itself, or to isolate the x. Now in this case, I could just erase the negative 9 from the left-hand side. That would get x by itself, but that's not legal from a mathematical perspective. The right thing to do to get x by itself is to add 9 to both sides of the equation. So I could start with x minus 9 equals negative 3 and just add 9 to both sides of the equation. It's sort of like adding 9 pounds to both sides of a seesaw. If I add 9 pounds to one side and 9 on the other, then the seesaw stays level, it stays balanced. And as long as I add the same amount to both sides, I'm good to go. So now I have x minus 9 equals negative 3. I add 9 to both sides, and the left-hand side just becomes x, because minus 9 plus 9 is just 0. And on the right-hand side, I have negative 3 plus 9, and that equals 6. And so what I'm left with is x equals 6, and 6 is my solution. Now, I can check the solution by plugging 6 into the original equation for x and confirming that the result is true. So let's do that pretty quickly. X minus 9 equals negative 3. That was the original equation. I'm going to plug in 6 for x, and I'll have 6 minus 9 equals negative 3, which is the same as just negative 3 equals negative 3. And of course, that's true. And that confirms that I really did have the correct solution when I was done. Now, I want you to notice that this is called a one-step equation because we only needed one step to complete it. I basically added 9 to both sides of the equation. That was the one step of work that I had to do. So let's try another one-step equation, and this time I want you to try it on your own. Let's solve x plus 3 equals 8. Now, here's my question. Did you get 5? Well, I hope so, because of course 5 plus 3 does equal 8. So 5 really is the solution to that problem. Now, let me show you another type of one-step equation, which is actually pretty different from the ones we just did. So here we go. Solve negative 7y equals 84. Now, just like in the previous examples, I want to get the variable, in this case y, alone. I want to get it by itself. This is always the goal when you're trying to solve linear equations. So I've got to get rid of that negative 7 somehow. And as I joked a moment ago, I could just take a pencil eraser and erase the thing, but that wouldn't be mathematically correct. So how do I get rid of that negative 7? Well, in this case, it's not addition or subtraction. So what would I do? Well, in this case, I need to divide. I need to divide both sides of the equation by negative 7. And when I do that, I'm going to have, on the left-hand side, negative 7y divided by negative 7. And on the right-hand side, I'm going to have 84 divided by negative 7. Again, it's perfectly legal from a mathematical perspective to divide both sides of an equation by the same number, in this case, negative 7. Now, what happens? Well, on the left-hand side of the equation, the negative 7s will cancel one another. And you and I will just have 1y, which is the same as y. And that's excellent because we've now isolated that y. We've gotten the y by itself. But what happens on the right-hand side? Well, we have 84 divided by negative 7. And when you compute that, or when you simplify that, you're going to get negative 12. And so the original equation now becomes y equals negative 12. And that's your solution. If you wanted to check it, you would plug negative 12 into the original equation and make sure that it's true. Now, in this case, I want you to try one of these kinds of one-step equations. So solve the following. 4y equals negative 36. Now, if you followed the way we worked on the previous example, you should have come up with negative 9 for an answer because you would have divided both sides by the 4. Now, that's two very special kinds of one-step equations that we've looked at so far in this lesson. And now I'd like to look at some slightly more complicated equations. Let's transition to talking about solving two-step equations. Things like 5x plus 4 equals negative 11. Now, before you start worrying about two-step equations, it turns out that they're not much harder than one-step equations. Basically, they're just two steps rather than one. Just think of them like one-step equations twice. In order to get that variable x on the left-hand side of something like 5x plus 4 to be by itself, I'm going to have to get rid of the 5 and I'm going to have to get rid of the 4. And that's why we call these two-step equations. But they're really not too bad. So let's look at how we would attack this problem. First, I'm going to get rid of the 4. Now, one very natural question that you might ask is, why are you getting rid of the 4 and not the 5? Well, Believe it or not, the answer to that question is wrapped up in order of operations, which we just saw in the previous lesson. To isolate that x, I have to undo the multiplication by 5 and the addition of the 4 in the opposite order, in reverse order. And so I'm going to start getting x by itself by getting rid of that 4. So to remove that 4, I'm going to subtract 4 from the left of the equation. But if I subtract 4 from the left side of the equation, I need to subtract 4 from the right side of the equation. Again, remember that seesaw idea I talked about earlier. And so that means I'll have 5x plus 4 equals negative 11, and I'm going to subtract 4 from both sides. The left-hand side will then just become 5x, because 4 minus 4 is 0. The right-hand side becomes negative 11 minus 4, which is negative 15. And so what I'm left with now is 5x equals negative 15. And something very, very important just happened. I started with a two-step equation. I'm down now to a one-step equation. 5x equals negative 15. It feels an awful lot like a couple of examples we just did. So how do we get rid of that 5? You know how. We're going to divide both sides by 5. And when I do that, starting with 5x equals negative 15 and dividing both sides by 5, the left-hand side will just be 1x, because the 5's will cancel, and the right-hand side will be negative 15 divided by 5. What is that when you simplify? It's negative 3. And therefore, the solution is going to be x equals negative 3. You and I just solved a two-step equation, no trouble at all. But let's check. Let's make sure that negative 3 really is the solution. So the original equation was 5x plus 4 equals negative 11. Let's plug negative 3 in for x, and let's see what we get. 5 times negative 3 is negative 15, so the left-hand side is negative 15 plus 4. What is negative 15 plus 4? It's negative 11. And the right-hand side was negative 11. Well, of course, negative 11 equals negative 11. That's a true statement. And therefore, we know that we had the correct solution when we finished that problem. Now, I'd like you to try to solve a two-step linear equation now. Remember that you'll need to add or subtract first, maybe multiply or divide after that. But let's try to work on this one, and maybe you try it first and see how you do. Let's try solving this equation. 3x minus 7 equals 5. Now, if you worked through the two steps, adding the 7 to both sides, then dividing by 3, you should have gotten 4 for your solution. And if you did, you got it right. Now, we've seen a number of examples of solving a linear equation. Now, I'd like to look at some more complicated examples so that you feel comfortable with some of the different ways that these problems can be presented to you. Now, you've already seen a number of examples, and we've worked through the one-step and the two-step equations. Remember, we're just going to be adding a few more steps. It's not much more complicated as long as we learn the steps and we learn to do them in the right order. We're mastering those basics. So let's look at the following example together. I want us to solve 3/4 x minus 2/5 x equals 14. Now, first things first in these kinds of examples, I don't want you to worry about those fractions. I see the fractions. You're probably worried about them, but we can handle them. In fact, one very straightforward way to handle them is to find a common denominator and then to add those fractions. But I'm going to actually share a slightly different idea, which is the same from the mathematical side, but it gets rid of the fractions from the beginning. I want us to start with the equation we had and multiply both sides of that equation by 20. So you're going to have 20 times the left-hand side, or 20 times 3/4 x minus 2/5 x. And on the right-hand side, you're going to have 20 times 14. If you multiply by 20 on the left, then you must multiply by 20 on the right. Again, it's like that seesaw we're keeping balanced. Now, why did I pick 20? I could have picked something else. Well, 20 is the least common multiple of 4 and 5. And it would be the least common denominator of the two fractions if we had gone the route of trying to subtract the fractions. So let's now distribute that 20 on the left-hand side and simplify both sides of the equation. When I do that, I'm going to have 20 times 3/4 x minus 20 times 2/5 x, and the right-hand side, 20 times 14, is 280. And now if I work through the products, 20 times 3/4 is 15, and 20 times 2/5 is 8. And that's going to leave me 15x minus 8x equals 280. Well, 15x minus 8x is 7x, because 15 minus 8 is 7. And so I have the equation 7x equals 280. Now that's a one-step equation. So what do? I know how to finish this problem. I divide both sides by 7, and I get x on the left-hand side, because 7 over 7 is 1. And the right-hand side is 280 divided by 7, and that's 40. And I'm left with x equals 40. And therefore, the solution of the equation that we started with is just 40. Now, here's one for you to solve. I want you to solve 1/3 x minus 3/4 x equals 10. Now, did you remember to multiply by 12 on both sides of that equation? If you did, it would have canceled out all of those fractions for you, and everything would have just become whole number arithmetic. And if you then work through the steps the way I did in the previous example, you should have obtained x equals negative 24 for an answer. Now, let's look at a different type of multi-step equation, just a little more complication. I want you to see as many different types of these linear equations as you can. Let's do the following. Solve negative 6 times the quantity b minus 4 equals 42. Now remember, the first thing I really want to try to do is to get that variable b by itself. I want to isolate that variable b. Well, how am I going to do that? Well, the first thing I want to do is to get rid of that negative 6 that's hanging out in front. That negative 6 is being multiplied by everything else on the left-hand side. The opposite of multiplication is division. And so the first thing I'm going to start to do is to divide both sides by negative 6. On the left-hand side, that's going to give me negative 6 times the quantity b minus 4 divided by negative 6. And on the right-hand side, I'm going to have 42 divided by negative 6. Well, the negative 6's on the left-hand side cancel, and I'm left with just b minus 4 on the left. And on the right side, I have 42 divided by negative 6, and that's negative 7. So the equation I now have has been cleaned up quite a bit. It's b minus 4 equals negative 7. Now, just a quick reminder, when you divide a negative number by another negative number, the sign of the result is going to be positive because the two signs you started with were the same. In this case, we took positive 42 and divided it by a negative number, and so the answer had to be negative. And that's why we have a negative 7 on the right-hand side. So we have b minus 4 equals negative 7. Well, that's just a one-step equation. I just need to get rid of that negative 4 on the left-hand side. How do I do it? I add 4 to both sides. And if I do, I'll have just b on the left, because minus 4 plus 4 is 0. They go away. And on the right-hand side, I have negative 7 plus 4, and that equals negative 3. So it looks like my solution is b equals negative 3. So for practice, let's check that that really is the solution. We started with the equation negative 6 times b minus 4 equals 42, and now let's plug in that negative 3 and see if it really is the solution. When I plug in negative 3 for b, I'm going to have negative 6 times the quantity, negative 3 minus 4, equals 42. Now remember our order of operations. We have to do what's inside the parentheses first. So the negative 3 minus the 4 gives me a negative 7. So the left-hand side now becomes negative 6 times negative 7 equals 42. And negative 6 times negative 7 is positive 42. 42 does equal 42. That works, and therefore I really did have the right solution. Now, I'd like to give you a chance to solve this kind of an equation, so let's do the following. solve 3 times the quantity z minus 1 equals 18. If you did everything in the right order and did it all correctly, you got z equals 7, and that's a great job. Now, let's transition to a new level of complexity with these problems. One of the common ways to really complicate matters is to see variables on both sides of a linear equation. Did you notice that in all of the examples we've done up to this point, there's only been one variable on one side? Well, we could mess things up a bit by having an equation like negative x plus 3 equals 5x plus 63. And now you would have an x on one side and an x on the other. How would we handle that? Well, it's really not a problem at all. The ultimate goal is to get all of the variables on one side of the equation and all the numbers or the constants on the other side of the equation. You've already seen all the tools that you need to do this. And by the way, you don't have to get the variables always on the left and the numbers always on the right. You can put them on either side. It's just that you have to get all the variables on one side and all the numbers on the other. So in this case, let's start by getting the constants over to the right-hand side. I've already got a 63 over there, so all I need to do is get that 3 that's on the left side moved over to the right. How do I get that 3 over to the right? Well, I subtract 3 from both sides. Remember, you've got to do it from both sides of the equation. The left-hand side then becomes just negative x, because 3 minus 3 is just 0. And the right-hand side becomes 5x plus 63 minus 3. 63 minus 3 is 60. And so the new equation I have is negative x equals 5x plus 60. Next, I want to get all those x's together, and I'm going to get them over to the left-hand side. I already have a negative x there. I just have to get that 5x to move over there. The way I do that, I subtract 5x from both sides. And now the left-hand side becomes negative x minus 5x, which is negative 6x. And the right-hand side becomes, well, 5x minus 5x, that's going to cancel away, and I'll just be left with 60. And therefore, my new equation is negative 6x equals 60. Remember, when I did that arithmetic on the left-hand side, negative x is the same as negative 1x. So what I was really doing there was negative 1x minus 5x, and that's the same as negative 6x, because negative 1 minus 5 is negative 6. Now, how do I get rid of that negative 6 and get it out of the way so that x is by itself? I'm just going to divide by a negative 6. We've done this kind of thing already in this lesson. So I now divide both sides of this equation by negative 6. And I've got negative 6x divided by negative 6 equals 60 divided by negative 6. Of course, the negative 6 on the left, they just cancel each other, leaving me with an x. That's great. And the right-hand side is 60 divided by negative 6, which is negative 10. So my solution is x equals negative 10. As long as we've done everything correctly, I say we check just to make sure that negative 10 really is the solution. So I had as the original equation, negative x plus 3 equals 5x plus 63. I now need to plug that negative 10 into all the x's that I see. I see one on the left, I see one on the right, so I plug in a negative 10 in both of those spots, and I have the negative of negative 10 plus 3 equals 5 times negative 10 plus 63. Negative of negative 10 is just positive 10, so the left-hand side is 10 plus 3, which is 13. And on the right-hand side, 5 times negative 10 is negative 50, and negative 50 plus 63 is positive 13. So I have 13 equals 13. That's true, and that means I had the right solution, which is fabulous. Now, I'd like to give you a chance again to solve a similar kind of equation. So let me give you one. Let's try solving 7x minus 4 equals 8 plus x. Go for it. See how you do. Well, if you walked through the same sorts of steps that I just did, you should have gotten x equals 2. That would be exactly right. Now, I'd like to remind you of two other types of equations and their solutions. So let me ask a really quick question. Have you ever noticed that all the linear equations we've discussed up to this point have had exactly one solution? When we've looked at a lot of equations, and every time we've had exactly one solution. Is that going to happen all the time? That's really a good question to ask. So let me give you a hint. It's not always going to happen that way. Let's look at the following example and see that other things can happen. Let's solve the following. 3 times the quantity, 7x minus 6, equals 21x plus 2. Well, I'm going to actually start by taking that 3 that's on the left-hand side and distributing it into the parentheses. And when I do that, I'm going to have 3 times 7x minus 3 times 6 equals 21x plus 2. And if I just simplify that left-hand side a bit, I'm going to have 21x minus 18 equals 21x plus 2. Now, if I wanted to get all those x's on the left-hand side, I would subtract the 21x on the right-hand side over to the left. And remember, if I subtract 21x from one side, I've got to subtract 21x from the other side. And what happens when you do that? Well, the 21x on the left goes away because 21x minus 21x is 0, or 0x. And on the right-hand side, the 21x will also go away because 21x minus 21x is 0x, which is 0. What does that leave me? Well, the left-hand side still has a negative 18, so it's still there, and the right-hand side still has a plus 2. So now I have the equation negative 18 equals 2. Now I want you to stop and think with me for just a second. Is negative 18 equal to 2? Never. Those are never equal to one another. So now you've got to wonder, wait, did we make a mistake? No, everything we've done up to this point is correct. And what does that mean? How do we interpret that? How do we think about this critically? Well, it means that the equation we started with can't have any solutions because we could never have had negative 18 equals 2. And so it's possible that some linear equations that you start with actually have no solutions at all. Sometimes they have one solution, sometimes they have none. All right, with that in mind, let's look at one more example. Solve the following equation. 3 times 7x plus 14 equals 7 times 3x plus 6. Well, I'm going to start this example the way I started the previous example. Let's distribute the 3 on the left into the parentheses, and let's distribute that 7 on the right into the parentheses as well. What do I have then? I'll have 3 times 7x plus 3 times 14 equals 7 times 3x plus 7 times 6. If you start to do some of the simplification there, you'll have 21x plus 42 equals 21x plus 42. Now, let's stop and think again for just a minute. Look at the left-hand side and look at the right-hand side. Those two things are equal no matter what you plug in for x. In fact, that means something very, very special. It means that every number that we can possibly plug in for x is a solution. And that means every real number, no matter whether you want to plug in 1 or 17 or negative 103, it doesn't matter. Every real number you plug in will be a solution. And that's basically the opposite of what we saw in the previous example. And it leads us to another vocabulary word for this course. We're going to say that an equation that is true for every possible value of the variable is called an identity. So in that last example that we just finished, the equation we started with is actually called an identity because anything you plug in for x is a solution of that equation. And this leads us to a big picture comment that's extremely important for this course. Every linear equation that you can write down falls into one of 3 categories. Either the equation will have exactly one solution, we saw that in a lot of examples already, or your equation will have no solutions at all, or the equation is an identity. Those are the only 3 options, but all 3 of them can occur. I've shown you examples of each of those 3 in this lesson. Now, I'd like to close the lesson with a quick word problem, so let's get right to it. We have a rectangle, and the length of the rectangle is 4 centimeters shorter than the width of the rectangle. The total perimeter of the rectangle is exactly 100 centimeters. I'd like us to find the length and the width of that rectangle. Well, let's start by defining some variables. Let's let x be the length of the rectangle. And that means the width then is x plus 4, because remember from the problem itself, the width was larger than the length by 4 centimeters. And that means that the perimeter equation is given by 2x plus 2 times the quantity x plus 4 equals 100. Remember, the full perimeter was supposed to be 100 centimeters. Now let's solve this equation for x. I'm going to start by distributing that 2 that's in front of the x plus 4 into those parentheses. And that's going to give me 2x plus 2x plus 8 equals 100. And that's the same as 4x plus 8 equals 100. If I subtract the 8 over to the right-hand side, I'll have 4x equals 92. 100 minus 8 is 92. And if I divide both sides by 4, I'll have x on the left equals 92 divided by 4, which is 23. So the length of the rectangle is 23 centimeters, and that means the width of the rectangle is 27 centimeters because it was supposed to be 4 centimeters longer. I can confirm that if I'd like by adding 23 plus 27 plus 23 plus 27, which is 50 plus 50, which is 100. And that was exactly what I was supposed to get for my perimeter. So with that example, I'm going to close this lesson on solving linear equations. Next time, I want to continue our discussion of solving linear equations, but I want to mix things up a bit. We're going to add some absolute value symbols into the equations, and we're going to see how we solve those. Those absolute value symbols change things a lot, but it's very straightforward to do. I look forward to talking with you about those in the next lesson. In the previous lesson, we spent some time talking about solving linear equations. My goal in this lesson is to take that a step further and to look at solving a very special set of equations which involve absolute values. Before we can start solving these equations, we need to spend a few minutes talking about what absolute values really are. And to do that, we have to go back to the idea of the real number line. Remember that the real number line is a way to see or to visualize the set of real numbers. It's usually drawn as a horizontal line with tick marks or vertical lines marking the locations of several numbers on the line. We often label the real number line with the 0 in the middle. And this point is very special to us. It sort of gives us a good way to start, and we give it a particular name. We call that place the origin on the number line. We can then label as many other points as we want on the line, and usually we pick a few whole numbers to label, maybe from -4 up to 4. Once that's done, we can now talk about the idea of the absolute value of a number. The absolute value of a number is most often written with 2 vertical lines, one on either side of the number. So, for example, the absolute value of 4 is written as a 4 with a vertical line on each side, while the absolute value of the number -5 is written as -5 with a vertical line on each side. But what does this symbol mean with these vertical lines? Well, to be honest, it doesn't mean anything more than the distance from the origin on the number line to that particular number. So, for example, absolute value of 4 means the number of steps we would have to go from the origin, or the 0, to the number 4. Well, that would be 4 steps. You'd have to start at the 0 and then just go 1, 2, 3, 4. So, absolute value of 4 is just 4. Well, how about the absolute value of -3? Well, how far is the number -3 from the origin on the number line? The answer is 3, because if we started at the origin, we'd have to go one step to the -1, then another step to the -2, and then a third step from -2 to -3. And that means that the absolute value of -3 is exactly 3. And I want you to notice that it's +3, not -3. So, what do we see from those two examples that I just mentioned to you? Well, first, the absolute value of any number is really just a distance more than anything else. And I think that's an extremely important way to remember absolute values. And the second important thing is that the absolute value of a number is always positive. Well, it's not always positive because the absolute value of 0 is just 0, and 0 is not usually thought of as a positive number. But the absolute value of every number other than 0 is always positive. So this is very important to remember. And thirdly, there's a way to write the absolute value in a sort of algebraic way so that you really don't need the vertical lines. That is, if x is greater than 0, then absolute value of x is just equal to x. While if x is less than 0, then the absolute value of x is equal to the negative of x. So, for example, when we did absolute value of -3 before, we saw that it was equal to 3. Well, another way to get that 3 would have been to take the negative of -3. And the negative of -3 is exactly equal to 3. So I can actually write absolute values without those lines if I really want, keeping these algebra rules in mind. Bottom line, if someone comes to you and says they've found an absolute value and it's equal to something like -2 or -7, you automatically know it's wrong. This is part of the critical thinking we need to do about absolute values. So let's move to a slightly more complicated example where I want to do an absolute value, but I need to do an absolute value of something that looks a little more complicated than just one number. Let's find the absolute value of 3 times the quantity 4 minus 15 plus 10. From what I know about order of operations, I know that I need to simplify what's inside the parentheses first before we can do anything else. So the first thing I'm going to do is compute 4 minus 15, and that gives me -11. And so the original problem is now whittled down to the absolute value of 3 times -11 plus 10. I then need to do the multiplication next, and that's going to give me absolute value of -33 plus 10. And that, of course, is the same as absolute value of -23. -33 plus 10 is -23. So now I know that I just want how far -23 is from the origin. That's what absolute value of -23 means. And the answer there is 23. So I know that the original number that I wanted, which was pretty complicated, absolute value of 3 times 4 minus 15 plus 10, is exactly equal to 23. Okay, let's move to another example of this type. Here now I want to start with an absolute value which has some variables in it, but I want to plug in a particular number for the variable and see what I get. Let's find the absolute value of -4x times x minus 3 squared when x is equal to -2. So the first thing I'm going to do is substitute the value -2 in for x throughout the expression. And when I do that, I'm going to have absolute value of -4 times -2 times the quantity -2 minus 3 squared. Now I've got to walk through my order of operations. The first thing I need to do is to simplify what's inside those parentheses. So that means I'm going to have absolute value of -4 times -2 times -5 squared. And after I've computed what's inside those parentheses, I now need to do the exponentiation. And that means I need to compute -5 squared. Well, -5 squared is -5 times -5, and that's equal to positive 25. So now what I'm down to is the absolute value of -4 times -2 times 25. I now perform those multiplications, And of course, negative 4 times negative 2, let's see, that's positive 8. Remember, when you multiply two negative numbers, you get a positive back. So I'm really down to absolute value of 8 times 25, which is the absolute value of 200. And this is 200 because the number 200 is exactly 200 units away from the origin. So my final answer is 200. Okay, with those examples done, I want to move to some more examples of solving equations, this time where the equations have absolute values in them. Now, these are going to be slightly different from just solving linear equations. They kind of look linear, especially if you don't look for those vertical lines, but once you've thrown those vertical lines in and you have absolute values, the problems get slightly different and a bit more difficult. They're not impossibly difficult, but they are different. So let's be careful as we walk through these examples. The first one I want to look at is this. Solve the equation absolute value of 2x minus 4 equals 14. Now, let's say something very, very important about this kind of equation that is true for all of these kinds of equations. There are lots of students who believe that the way to do this kind of a problem is just to erase the absolute value symbols and just to solve the equation 2x minus 4 equals 14. It turns out that this isn't really a bad idea, but it's not the whole idea. It's only half of the solution of the problem. What you really have to do to solve the problem correctly and completely is to actually convert the original equation into two separate equations. And you have to solve 2x minus 4 equals 14, and you have to solve 2x minus 4 equals negative 14. Why? Why do you have to do that second equation, 2x minus 4 equals negative 14? Well, it's because when we say absolute value of 2x minus 4 is 14, we're saying that the quantity 2x minus 4 lives either 14 steps to the left of the origin or 14 steps to the right of the origin on the number line. So actually solving the equation absolute value of 2x minus 4 equals 14 is really solving two different problems. Now, if you think you've got the idea, why don't you stop the video at this time and see if you can solve those two equations from here. Well, do you think you got the right answers? Let's look at them ourselves now. Let's attack the two problems separately and see what you get. We start by solving 2x minus 4 equals 14. If I add 4 to both sides of that equation, I'm going to have 2x equals 18. And now if I want to get that x by itself, I just divide by 2, and I will have x on the left equals 9. So it looks like x equals 9 is a solution. Let's check by plugging 9 back in for x in the original equation. That's going to look like absolute value of 2 times 9 minus 4, which is the same as absolute value of 18 minus 4, which equals absolute value of 14, which is 14. And that was the right-hand side of what we started with. So that's fabulous. But we're not done. We've only done half the problem. The original equation could also be 2x minus 4 equals negative 14. Now let's solve that equation and see what we get. Well, 2x minus 4 equals negative 14 is the same as 2x equals negative 10. How do I get negative 10? I add 4 to both sides of the equation. And from 2x equals negative 10, I can convert to x equals negative 5 by dividing both sides by 2. So it also looks like I have a second solution, x equals negative 5. Let's check that by plugging negative 5 into the original equation. When I do that, I have absolute value of 2 times negative 5 minus 4, which is absolute value of negative 10 minus 4, which is absolute value of negative 14, and the absolute value of negative 14 is 14. And that was the right-hand side of the original equation, so negative 5 really is a solution as well. And it turns out that our original equation then has two solutions, not just one. X equals 9 and x equals negative 5 are both solutions. And that's fabulous. It turns out that finishes that example. Both of those numbers really are solutions. Now, before I go to another example, I need to emphasize one point quite a bit, and here it is. It's extremely important in these kinds of problems that we check all of our solutions to make sure that they really are solutions. Believe it or not, there are lots of ways that sort of false or phony solutions can pop up in these problems. Not because we've done anything wrong, but because of the way the problems are done. You can actually have some false solutions. The only way to know whether we have all of the correct solutions is to plug those numbers back into the original equation to make sure they really work. So although it takes some time and sometimes it's a bit tedious, let's make sure we plug those answers back in to confirm that they really are solutions before we move on to the next problem. So with that in mind, I want you to try solving one on your own and check both answers to see if they work. Here's an example I want you to work on. Solve the following equation. 4 times the absolute value of 3x plus 1 minus 7 equals 13. Now, did they both work? Well, I'll tell you, let's try solving it together and let's make sure that I get the same solutions that you did. So this equation actually requires a little bit of rewriting before we really find the solutions. And that rewriting basically means that I want to get the absolute value symbol by itself. So let's start with the original equation and do some things, some algebra that's legal to do to get the absolute value by itself. We started with 4 times absolute value of 3x plus 1 minus 7 equals 13. Let's add 7 to both sides to give me 4 times absolute value of 3x plus 1 equals 20. And now I can divide that 4 from both sides of the equation. And when I do that, on the left-hand side, it'll go away. I'll have absolute value of 3x plus 1. And on the right-hand side, I'll have 20 divided by 4, which is 5. So I'm now down to an equation, absolute value of 3x plus 1 equals 5. Now, from the example that I just did a few moments ago, we know that this is really 2 different linear equations. Either 3x plus 1 equals 5, or 3x plus 1 equals negative 5. So now I need to solve each of these one at a time and check the answers to make sure that they really are solutions of the original equation. So the first equation was 3x plus 1 equals 5. If I subtract 1 from both sides, I'll have 3x equals 4. And dividing both sides by 3, I have x equals 4/3. Did you notice how we just solved a 2-step equation just like we did a few lessons ago? It's great. This stuff is building on itself. We're mastering those basics. So one possible solution is x equals 4/3. Now remember, the other equation was 3x plus 1 equals negative 5. Subtracting 1 from both sides gives me 3x equals negative 6. Dividing by 3 gives me x equals negative 2. So I have 2 possible solutions. X equals 4/3 and x equals negative 2. Let's check that each of these is a solution by plugging them back into the starting equation. The original equation was 4 times absolute value of 3x plus 1 minus 7 equals 13. If I plug in 4/3, I have 4 times absolute value of 3 times 4/3 plus 1 minus 7 equals 13. And the material inside the absolute value simply becomes 4 plus 1. 3 times 4/3 is just 4. So what I really have is 4 times absolute value of 5 minus 7 equals 13. Absolute value of 5 is just 5, so I have 4 times 5 minus 7 equals 13. 20 minus 7 equals 13, or 13 equals 13. And since 13 equals 13, I know that what I plugged in the beginning, x equals 4/3, really is a solution. Now, let's try plugging in the other value, x equals negative 2. Well, if I do that, I'll have 4 times absolute value of 3 times negative 2 plus 1 minus 7 equals 13. 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5. And so what I now have is 4 times absolute value of negative 5 minus 7 equals 13. Remember, absolute value of negative 5 is positive 5. So now I have 4 times 5 minus 7 equals 13. That's 20 minus 7 equals 13, which is 13 equals 13. And that works. So x equals negative 2 is also really a solution. Now I have to ask you, is that what you found also? I hope it is. Both of those numbers really are solutions. Now, let's move to some other equations that come up in this kind of work, again, where you have absolute values floating around in an equation. Let's solve the following example. Absolute value of 7x minus 19 equals negative 10. Now, we need to be a bit careful and think about this equation for just a second. Let's do some of that critical thinking together. Notice that the left-hand side of this equation is just one big absolute value. And we know that no matter what's inside the absolute value symbols, the absolute value either is 0 or a positive number. But look at the right-hand side of the equation. It's a negative number, negative 10. So the left-hand side is either 0 or something positive, while the right-hand side is negative. What do we conclude? What's the answer then? We know then that the original equation has no solutions because there are no numbers which are both positive and negative at the same time. So that equation actually had no solutions, and that's a possibility. We've already seen examples of equations in a previous lesson where we had no solutions. The same sort of thing can happen with these absolute values. Now, let's look at another example where the variable x shows up in more than one place. This can easily happen. So let's try the following. Solve absolute value of 6x minus 2 equals 5x plus 3. Now, let's go back to one of the main ideas in this lesson, that this kind of equation has to be broken into two separate equations. The first one is just 6x minus 2 equals 5x plus 3. That's the one you get when you basically erase those absolute value symbols. But remember, you're not erasing them, you're simply thinking of that piece as positive. But the other equation that can come up with is 6x minus 2 equals the negative of the right-hand side. So we would have 6x minus 2 equals the negative of 5x plus 3. Notice that the negative sign on that right-hand side of the second equation has to impact both the 5x and the 3. In other words, I don't want to write down negative 5x plus 3 for the right-hand side, because that's very different from negative quantity 5x plus 3, which actually equals negative 5x minus 3. So I now have my two equations. Let's solve each of those two equations separately and see what we get. The first equation was 6x minus 2 equals 5x plus 3. If we move the 5x over to the left, or just subtract 5x from both sides, we will have x minus 2 equals 3. And now adding 2 to both sides of that equation gives me x equals 5. So one of the possible solutions is x equals 5. Now if I go to the second equation I had written down, which was 6x minus 2 equals the negative of 5x plus 3, I'm looking at 6x minus 2 equals negative 5x minus 3. Adding 5x to both sides gives me 11x minus 2 equals negative 3. Adding 2 to both sides of that gives me 11x equals negative 1. And if I just divide by 11, I have x equals negative 1 over 11. And that gives me a second possible solution. So I have x equals 5 and x equals negative 1 over 11 as potential solutions. The only way we can confirm or guarantee that they really are solutions is to plug them back into the original equation and see if they work. So let's do that now. Let's start with the first of the possible solutions, x equals 5, and plug it in. I'll have absolute value of 6 times 5 minus 2 equals 5 times 5 plus 3. On the left-hand side, I'm going to have absolute value of 30 minus 2, which of course is absolute value of 28, which is just 28. On the right-hand side, I have 5 times 5 plus 3, which is 25 plus 3, which is 28. And that means that the left-hand side and the right-hand side are both 28. And that's true, and therefore, x equals 5 really is a solution of the original equation. That's good to go. Now let's try the other potential solution, -1/11. Well, the arithmetic's going to get a bit messy, but it's okay. We can work our way through it. Here I'm going to have absolute value of 6 times -1/11 minus 2 equals 5 times -1/11 plus 3. The left-hand side becomes absolute value of -6/11 minus 2. Getting a common denominator gives me absolute value of -6/11 minus 22/11. And now if I look at my right-hand side for just a second, I've got -5/11 plus 3. Again, getting a common denominator is going to give me -5/11 plus 33/11. Now, if I simplify both sides of that equation for just a moment, the left-hand side becomes absolute value of -28/11, and the right-hand side becomes 28/11, and both of those sides are just equal to 28/11. That means that x equals -1/11 is also a solution. So both of those numbers really were solutions. Now I'd like you to see if you can solve one of these on your own, and let me give it to you here. Solve absolute value of 3x plus 5 equals 5x plus 2. Now let's do it together, and let's see if the numbers you got were correct. Again, I'm going to split this into two equations, and I'm going to solve each one separately. And those two equations are going to be 3x plus 5 equals 5x plus 2, or 3x plus 5 equals the negative of 5x plus 2. Let's do these separately now. 3x plus 5 equals 5x plus 2. If I subtract 3x from both sides, I get 5 equals 2x plus 2. Subtracting 2 from both sides now gives me 3 equals 2x. Now you might be saying, wait a minute, your x is on the right-hand side. Remember in a previous lesson I talked about how the x's could be on one side, the numbers could be on the other. It doesn't matter which is which. So 3 equals 2x, no problem. Now divide by 2 on both sides, and you'll basically have x equals 3/2. That's one possible solution. Now let's look at the other equation. 3x plus 5 equals the negative of 5x plus 2. That's the same as 3x plus 5 equals negative 5x minus 2. Make sure that that negative sign gets distributed all the way through the parentheses. And now if I add 5x to both sides, I'll have 8x plus 5 equals negative 2. And if I subtract 5 from both sides, I'll have 8x equals negative 7. Dividing by 8 gives me x equals negative 7/8. So now I have two numbers that are potential solutions. I've got to plug them in to see if they really are solutions. So I plug them back into the original equation. The first one is absolute value of 3 times 3/2 plus 5 equals 5 times 3/2 plus 2. Well, what's that going to give me? Well, the left-hand side is absolute value of 9/2 plus 5, and that equals 15/2 plus 2. And now I need to get a common denominator, which is not a problem. That's just going to be a 2 all the way through. And the left-hand side becomes absolute value of 9/2 plus 10/2, and that equals the right-hand side, which is 15/2 plus 4/2. Now let's do some simplifying. The left-hand side is the absolute value of 19 divided by 2, and the right-hand side is just 19 divided by 2. And both of those sides are just equal to 19 divided by 2, or 19/2. And that means x equals 3/2 really is a solution of the original equation. And now let's try that other number. Let's see if it was also a solution. Well, if I plug in negative 7/8 into the original equation, I have absolute value of 3 times negative 7/8 plus 5 equals, on the right-hand side, 5 times negative 7/8 plus 2. And now let's do some simplifying. The absolute value on the left is going to be absolute value of negative 21 over 8 plus 5. Right-hand side becomes negative 35 over 8 plus 2. Let's get that common denominator. Now in this case it'll be 8s all the way across. And when you do that, you'll have absolute value of negative 21 over 8 plus 40 over 8 equals negative 35 over 8 plus 16 over 8. Now let's simplify. The left-hand side is absolute value of 19 over 8. The right-hand side is negative 19 over 8. But since absolute value of 19 over 8 is 19 over 8, I now have the equation 19 over 8 equals negative 19 over 8. We've done everything correctly. So what do we conclude? We conclude that the number I just plugged in, negative 7/8, is not a solution of the original problem. I like to think of these as false solutions, if you will. But false solutions are not solutions. You don't want to keep x equals negative 7/8. So what this means is that we really only had one real solution. And we're going to call this x equals negative 7/8, which is a phony solution, a special name. We're going to call it an extraneous solution. An extraneous solution is a solution of an equation which came from an original equation, but is not the solution of the original. So we don't want to keep this x equals negative 7/8. It's not a real solution of the original equation. And that means that there's really only one solution to keep, and that's x equals 3/2. Now you can see why I kept saying, we've got to check answers, we've got to check answers. Sometimes, even when we've done everything correctly, these false solutions or extraneous solutions try to sneak in. We have to watch for them, and we have to throw them out. Now, to finish this lesson today, I want to solve one more equation of this type. So let's do this one. Solve absolute value of x minus x equals 2. Well, let's do the first thing first. Let's get that absolute value term by itself. Add the x to the right-hand side, and you'll have absolute x, or absolute value of x, equals x plus 2. So we're trying to solve two equations. X equals x plus 2, and x equals the negative of x plus 2. That's always what you need to do with absolute value equations. The first equation, x equals x plus 2, gives you just 0 equals 2 when you subtract x from both sides. Okay, 0 is not equal to 2, so that equation is not going to give you a solution at all. The other equation that we had gives us something better. X equals the negative of the quantity x plus 2 is the same as x equals negative x minus 2, which is 2x equals negative 2, or x equals negative 1. Let's quickly check that x equals negative 1 is a solution. Let's see. I'll have absolute value of negative 1 minus negative 1 equals 2. That's the same as 1 minus negative 1 equals 2, since absolute value of negative 1 is 1. And that's the same as 1 plus 1 equals 2, or 2 equals 2. And since that checks, we know that x equals negative 1 is our one and only one solution of the original equation. Well, in this lesson, we've talked about absolute values and how to solve equations that involve them. Next time, I want to talk about linear equations and functions and look at the graphs of these things, and also look at parallel and perpendicular lines. I look forward to talking with you then. In this lesson, I would like to shift our focus a bit and review material on linear equations and functions, especially as it relates to the connection between the equations themselves and what the graphs look like. It's very important that we remember that algebra is much more than solving equations and manipulating algebraic expressions. In particular, it's critical that we keep the visual or graphing side in mind as we study algebra. In this lesson, I want to touch on three main subjects: the slope-intercept form of a line, the point-slope form of a line, and the special pairs of lines that we call parallel and perpendicular lines. So let me remind you of the definition first of the slope-intercept form of a line. If m is the slope of a line and b is the y-intercept of the line, then the slope-intercept form of the equation of a line is y equals mx plus b. Here's the picture you might want to have in mind. You're going to have a y-intercept in most cases where the line crosses the y-axis. In this case, the y-intercept is at the point 0, 1. And remember, the value m is going to be a number. That's going to be the slope of the line in question. Sometimes you've heard people refer to the rise over run, for example. So we'll talk more about slope as we walk through the following examples. Here's our first one. Let's find the slope-intercept form of the equation of this line. In order to do this, let's write the slope-intercept form once we have found the slope and the y-intercept. That's why it's called the slope-intercept form. And let me point out that we only need the y-intercept when we're writing down the slope-intercept form. We don't need to worry about the x-intercept, the place where the graph crosses the x-axis. We only need to know the y-intercept. Well, if you look at the graph, the y-intercept here is easy. It's just b equals 3 because the graph is going through the point 0, 3. Now let's figure out the slope. We need to know this rise over run, the change in the y direction divided by the change in the x direction. To do this, let's pick any 2 points on the line. Any 2 will do, and we can use those to find the slope. So I'm going to use 0, 3, that was that y-intercept, and the point 1, 5. And then with those 2 points, I can find the slope. The slope, which we often call m, is going to equal 5 minus 3 divided by 1 minus 0. That's the change in the y values, or the difference in the y values, divided by the difference in the x values. When you do a little simplification, the numerator is 2, the denominator is 1, so the slope here is equal to 2. And that means that the equation of this line, which is y equals mx plus b, is exactly y equals 2x plus 3. Okay, let's look at a second example of this form. Let's determine the slope-intercept form of the equation of this line. Well, here I see the y-intercept very quickly again. It's just b equals 1. That's because the place where this line crosses the y-axis is exactly the point 0, 1. So now we need to figure out the slope. What is that? Well, we know it has to be negative because the line is going down as we look at it from left to right. In other words, as we read it left to right, the line is actually going down. And that means the slope has to be negative. It's also got to be pretty small because the line is somewhat flat. It's not exactly flat. We would call that horizontal, but it is kind of flat. So our slope is going to be negative, and it's probably going to be pretty small. Now, let's calculate it. I need 2 points again. And if I look at my graph, I can see that the line goes through 4, 0, and 0, 1. Those are the 2 intercepts, the x-intercept and the y-intercept. And once I use that information in the formula for slope, I'm going to have the following. M equals 1 minus 0 divided by 0 minus 4, which is the same as 1 over negative 4, or negative 1/4. That's negative, and it's also relatively small. 1/4 is a pretty small number, and that means we're probably in the right ballpark. And if we use that information to find the slope-intercept form of the equation, we will have y equals negative 1/4 x plus 1. That's the equation we wanted. Now, let's transition a bit. What about if we wanted to do the opposite kind of problem? That is, if I give you the slope-intercept form of the equation first, could we figure out how to draw the graph? That would be sort of the opposite problem to what we've just done. Now, I have to admit, the slope-intercept form of a line seems to be the most popular one among lots of students and even among teachers. But I'm not sure why that is, because maybe it's the simplest form of the equation of the line that you can find. But let me be honest with you. In almost every example that I showed you so far, the y-intercept was basically handed to us. You could see it very, very clearly on the graph. What if that value b, which is where the y-intercept is located, hadn't been so obvious? What if it had been like b equals 1/19 or b equals 7/3, it might not have been so clear, and we would have had much more work to do to find that intercept. So that's a disadvantage, a problem when you want to use the slope-intercept form of the equation of a line. If b isn't basically handed to us, then it's very difficult to write down the slope-intercept form of that equation. So what do? Do we just give up and quit? No, we need to think about this slightly differently. It turns out we can learn another form of the equation of a line which doesn't require us to find the y-intercept first. And that leads us to something called the point-slope form of a line. Let me show you an example to try to motivate why this point-slope form of a line is very useful. So here's the example I want us to do. Find the equation of the line that's given to us here. Now, let me be clear about what we know. We see that the line goes through the point 2, 0. That's the x-intercept of the line. Let's assume we're also told that the line goes through the point -2, 10/3. From here, just having those 2 points, I want to work out the equation of the line. Well, with the 2 points that we're given, we can calculate the slope. Remember, the slope simply needs 2 points. It doesn't matter what the 2 points are, it just needs 2 points. So in this case, the slope is going to be 10/3 minus 0 divided by -2 minus 2. And that's the same thing as 10/3 in the numerator divided by -4, which is the same as -10/12 or -5/6. Notice that that's a negative slope, and from the picture we see, it should have been negative because again, the line is going down as we read from left to right. Now, that's one piece of information. We know the slope. Now we need one more piece of information. If we want the slope-intercept form of this line, we would have to find the y-intercept. But what is it? If you look at the graph of this equation that was given to us, it's very difficult to see the y-intercept because it looks like it's going between two whole numbers. It's obviously something between 1 and 2. Is it 1.5, 1 1/3, 1 2/3, 1 4/7? I don't know. It's just not clear. And that's the downside of the slope-intercept form of the equation of a line. If you can't find the y-intercept easily, or if it's not given to you, then the slope-intercept form is a bit unfriendly. Now, don't get me wrong, we could find that y-intercept with a little bit of algebra, but I claim that there's a better form of the equation that we can write down. And that's the point-slope form of the equation of a line. And that's what I want us to now think about as we move forward with this lesson. So, to get us started thinking about this, let's talk about the point-slope form of the equation of a line and write down its definition. Here we go. The point-slope form of the equation of a line that passes through any point, let's call it x1, y1, and has a slope m, is given by y minus y1 equals m times x minus x1. This is an extremely important formula, and you should put it to memory as soon as this lesson is over. In fact, you might even want to spend a few moments memorizing it right now. Y minus y1 equals m times x minus x1. Now, let's point out the x1 and the y1 were parts of the point that we already knew we had. The x and the y are variables in themselves. Now, with this form of the equation of a line available to us, we can now write down the equation of the line that we were talking about a few moments ago. Remember, we figured out that the slope was equal to -5/6, and we know that the line goes through the point 2, 0. That's the x-intercept, not the y-intercept. So thanks to the point-slope form of the equation of the line, we know that that equation is equal to the following. Y minus 0 equals -5/6 times the quantity x minus 2. The negative 5, 6 came from the slope, and the 2 and the 0 come from the point that we know the line goes through. Now, we could leave the equation that way. That could be our final answer if we wanted, or we can simplify it a bit. I'd like to simplify it just a bit with you and show you something thanks to all that simplification. So we have y minus 0 equals negative 5, 6 times the quantity x minus 2. Of course, y minus 0 is just y, so I can rewrite this as y equals negative 5, 6 times the quantity x minus 2. And now I can use the distributive property to give me y equals negative 5 6x minus 2 times negative 5 sixths. That's the same as y equals negative 5 6x plus 10 over 6. 2 times 5 gives me 10. And the negative times the negative gives me a positive. And if I simplify that just a little bit more, I get y equals negative 5 6x plus 5/3. Now, what's so special about the formula that we just wrote down? What is true about that equation? It's the equation of the same line we've been talking about, but notice that it's now in the form y equals mx plus b. That's the slope-intercept form of the line, and it's the same one we've been discussing. So now I know where that y-intercept really was. It was at 5/3, and that means it was at 1 and 2/3. Remember, the point looked like it was between 1 and 2. Now we know exactly where it went through. It went through 1 and 2/3. So I see that this point-slope form of the equation, it feels a little more flexible to me than the slope-intercept form. And that's because I can use any point that's on the line and the slope to find that equation. So once I can use that point-slope form, if I really, really want to know the y-intercept, I can convert it to slope-intercept form the way I just did to find the y-intercept of 5/3 in that example. Now, let's move on to another example where we can use the point-slope form of the equation of a line to our advantage. Now, what I'd like to suggest you do is stop the video and see if you can find the point-slope equation for this line yourself first. Let me give it to you. Write down the equation of the line that has slope 5 that passes through the point -1, -3. Now, with the slope-intercept form of the equation, you'd have some difficulty because the problem didn't tell you anything about the y-intercept. The point that we know the line is going through is nowhere near the y-intercept. But with the slope and with any point, I can use the point-slope form of the equation of a line to write down this line's equation. So here we go. Let's check to see if you got the work that I'm about to show you. The point-slope form of the equation of this line is y minus -3 equals 5 times the quantity x minus -1. And if I wanted to get rid of some of those minus signs, I know that a negative times another negative is a positive, and that means the point-slope form of the equation of this line can also be written as y plus 3 equals 5 times the quantity x plus 1. Remember that that 5 is going to have to be multiplied with both the x and the 1 if you decide to do any other work to simplify this equation. Now, if you got that equation, y plus 3 equals 5 times the quantity x plus 1, great job. You did it right, and you can move forward then. Now, let me make a couple comments as we continue on with these ideas of lines and their graphs and the equations of lines. First of all, a very common mistake that's made by some students is to switch the roles of the x-coordinate and the y-coordinate of the point they have when they're writing down the point-slope form of a line. So instead of writing y minus -3 equals 5 times the quantity x minus -1, like we just did in that example, some students will accidentally write down y minus -1 equals 5 times the quantity x minus -3. Do you see how the -1 and the -3 got switched when we did that incorrectly? You have to be very, very careful not to make this mistake, because in almost every instance, you're going to get the wrong equation if you accidentally make that flip. So be really careful where the y goes and where the x goes from your point. Now, secondly, as I mentioned a few minutes ago, once you have written down the point-slope form of the equation of a line, you can actually write down the slope-intercept form of the equation of that same line, if you want to, or if you're asked to do that. So let me suggest that we try converting the line we just wrote down, the point-slope form of that equation. Let me suggest that we try to convert it to slope-intercept form. So here's that equation again. Y plus 3 equals 5 times the quantity x plus 1. See if you can convert that to slope-intercept form. Well, here's how I would do it. I'd start with y plus 3 equals 5 times the quantity x plus 1. I then have to multiply that 5 through the parentheses using the distributive property. We've done that several times now in our earlier lessons. And that's going to give me y plus 3 equals the quantity 5x plus 5. Now I'm going to subtract 3 from both sides to get that y by itself. And when I do that, I'll have y equals 5x plus 5 minus 3, which is the same as y equals 5x plus 2. So let's just point out quickly before we move on. We now have the slope-intercept form of that same line we were discussing earlier. It turns out actually it had a pretty friendly y-intercept. That y-intercept would have been at 2, right through the y-axis, or if you wanted to worry about the point, it would have been the point 0, 2. So we know the slope was 5, which we knew already, and now we know from the slope-intercept form of this line that the y-intercept was at 2. Now, I'd like to transition a bit to another part of this review lesson, which is on parallel lines and perpendicular lines. First, let me talk about parallel lines by remembering the following property. So this is very important. Basically, this is the definition for parallel lines. Two non-vertical lines are parallel if they have the same slope and they have different y-intercepts. Now let me just unravel that definition really quickly. So two lines are going to be parallel if they have the same slope, but of course they also need different y-intercepts, because if they actually had the same y-intercept and the same slope, they would be the same line. So in order for two lines to be parallel, they need to have the same slope, but they have to cross the y-axis at different places, so they need to have different y-intercepts. One other quick comment about that definition. It said two non-vertical lines. Obviously, if you have two different vertical lines, they will also be parallel. But the reason the definition didn't talk about those is because vertical lines have undefined slope. They actually don't have a slope that we can write down as a number. So two vertical lines that are different will also be parallel, even though the definition doesn't talk about that. So, for example, if I take the lines y equal 3x plus 2 and y equals 3x minus 4, I see that they both have the same slope. That's pretty obvious thanks to the slope-intercept form of these two equations. They both have slope 3. Notice that they have different y-intercepts. The first one has a y-intercept at 2, which is above the origin, and the second line is going to have a y-intercept at -4, which is actually below the origin. So these two lines have the same slope. That means they're going in the same direction, but they have different y-intercepts. And therefore, by the definition, we know they're parallel. If I was to graph these two equations on the same set of axes, the fact that they're both parallel is very obvious. They both have the same slope of 3, but they're going to be separated from one another because their y-intercepts are different. Now, let's look at another quick example to see if we can spot parallel lines. Here's the example. I want you to determine whether the lines given by y equals -2x plus 7 and 10x plus 5y equals 12 are parallel. It's simple enough. I have two equations. They're both equations of lines. Can I tell if they're parallel? Well, to do this problem, I need to know the slope of each line first. I need to make sure that their slopes are the same. Well, it's very clear from the slope-intercept form of the first equation that the slope of that line is -2. We can see that -2 pretty quickly. But what about the slope of the second line? I'm going to need to rewrite that equation a bit using some algebra in order to write it in slope-intercept form. So let's do that now. We had 10x plus 5y equals 12. I want to write this thing as y equals mx plus b. So I'm going to subtract the 10x from both sides first. When I do that, that's going to give me 5y equals -10x plus 12. Now I don't want that 5 in front of the y, so I'm going to divide both sides by 5, which by the way is the same as multiplying both sides by 1/5. So in fact, I suggest we multiply both sides of the equation by 1/5. On the left, we'll have 1/5 times 5y, which of course is just 1y. 1/5 times 5 gives me 1. So the left-hand side becomes y. That's great, because that's getting me towards y equals mx plus b. Now the right-hand side has a 1/5 times the quantity, -10x plus 12. That 1/5 has to be distributed into those parentheses. So I need 1/5 times -10x plus 1/5 times 12. And when I simplify that a bit, I'm going to have -2x plus 12/5, 12 divided by 5. So I have y equals -2x plus 12/5, and that tells me that the second line has slope -2. Hey, that's a good thing because the slope of the first line was also -2. So these guys are really good candidates for parallel lines. They have the same slope, -2, and they have different y-intercepts. The first one has a y-intercept of 7, and the second one has a y-intercept of 12/5. So by my definition, I know that they really are parallel. Now, let's transition a little bit to another concept, this time the concept of perpendicular lines. So what does it mean for two lines to be perpendicular to one another? Well, from a visual perspective, it means that the two lines intersect one another at right angles. So that's a nice way to see it, but how do you recognize when two lines are perpendicular if all you have is the equations? It's a little hard to see those right angles when all you're staring at is equations of lines. Well, here's a really nifty property to tell from the equations whether two lines are perpendicular. It says the following: two lines are perpendicular if the product of their slopes equals -1. That is, if the slope of one of the lines is what's called the negative reciprocal of the slope of the other line. So, those are big words. Let's just look at a quick example. Take these two lines, y equals 4/7 x minus 3, and y equals -7/4 x plus 8. Those two lines are perpendicular if you use the property I just mentioned. Why? Look at their slopes. The one has a slope of 4/7, and the other one has a slope of -7/4. Do you see how those are reciprocals of one another, and one of them is positive and one of them is negative? In fact, the -7/4 is the negative reciprocal of the 4/7. And if I were to multiply those two numbers together, I would actually get -1. The 4s would cancel and the 7s would cancel, and I would just have -1/1 or -1. So if you look at a sketch of the graphs of these two lines, you'll actually see this nice right angle crossing between the two, and that shows us that these two lines are perpendicular. Now, I suggest we work through an example now just to make sure we've got this nailed down. Let's find an equation of a line which is perpendicular to the line given by y equals 2/3 x minus 1 that has y-intercept 0, 4. Okay, so let's be careful. We want a line which is perpendicular to y equals 2/3 x minus 1, and we want that line to go through the y-intercept 0, 4. All right, I would suggest that to find the equation here, we ought to use the slope-intercept form of the line because we were given the y-intercept. It makes it really easy. So the line I want is going to have an equation that looks like y equals mx plus 4 because the y-intercept is 4. Great. How do I find m, the slope of this line? Well, the slope of my new line needs to be the negative reciprocal of the slope of the line that was given to us. Remember, two lines are perpendicular if their slopes are negative reciprocals of one another. The slope of the line that was given to me is 2/3, and that means the slope of my new line needs to be negative 3/2. And now I know what m is. It's negative 3/2, and that means the equation of the line that I wanted is y equals negative 3/2 x plus 4. Again, a quick sketch of these two lines is probably a wise check of our work. And if you look at those two lines, you'll see this wonderful right angle crossing that occurs because these two lines are perpendicular. Now let me make a quick comment because I skipped over vertical lines again in talking about perpendicular lines. It's also going to be true that a vertical line and a horizontal line will always be perpendicular as well. Even though the vertical line has undefined slope, so I can't really talk about a negative reciprocal of that, it's still the case that a vertical line and a horizontal line will always be perpendicular because they connect at right angles. Now, today we've gone pretty quickly through a review of the different ways that you can represent linear equations. I talked about the slope-intercept form, which is a wonderful way to write down the equation of a line, but it has some problems if you don't know what the y-intercept is. I also talked about the point-slope form, which provides us with some flexibility because it allows us to know the slope and any point on the line in order to write down the equation of the line. And we also talked about these very special lines that we call parallel and perpendicular lines. And we'll try to have more practice with those in the coming lessons in order to practice with the way these equations really look to spot parallel and perpendicular lines. Next time I want to talk in some more general terms about some very important tools for drawing graphs of lots of different functions. As we walk through this course, not only will graphs just be straight lines, but we'll have a lot of curvature to our graphs as well. And I want us to talk about some of the tools we can use to shift from the graph of one function to the graph of another function. I think that's going to be a really interesting and eye-opening lesson, and I look forward to talking about it next time. In our previous lesson, we started talking about graphing techniques, especially related to straight lines. In this lesson, I'd like to continue talking about graphing and touch on two main points throughout the lesson. First, we'll talk about how to graph a line given its equation. And I want to do several examples of this to make sure we've got it down. We'll even talk about how to graph horizontal lines. And basically, this will be the opposite of what we were doing in the previous lesson. We'll be given the equation and we'll be asked to draw the straight line that corresponds to it. The second main topic that we'll talk about is how we can create one graph from another graph by shifting it around or flipping it around. And we'll see how the algebraic equations are changed in order to make these graphs move from one to the other. So let's start with some examples of lines whose equations are in slope-intercept form and see if we can actually draw the corresponding graphs. So if you'd like to try graphing some of these equations on your own first, just feel free to stop the video when you see the cue and start it again when you're ready. Otherwise, you can just watch and try to follow along as I work through these problems. So here's our first example. Sketch the graph of the equation y equals 5x minus 7. So we know that this is in slope-intercept form because it's of the form y equals mx plus b. And that means we can immediately spot the y-intercept. The b value, if you will, is equal to -7. So I know I can go plot one of the points right away. That's going to be the y-intercept at the point 0, -7. So I plot that point, and now we just need one more point in order to sketch the line. Remember, once you have two distinct points that the line passes through, you can simply plot those 2 points and just connect the dots. So what I want to do is now use the slope of the line to find a second point on the line. We know the slope is 5, which is the same as 5/1. And that's the ratio that we often call rise over run. So if we were to move over to the right 1 unit, we would have to move up 5 units. So if we start at that y-intercept that we've already plotted, 0, -7, move 1 unit over to the right and 5 units up, we're going to get to a second point, and that's going to be the point 1, -2. Once I connect those dots, it gives me exactly the sketch that I wanted. Okay, let's complete a different example that's still of this type, just to make sure we've got it down. If you'd like, try sketching this equation first before I show you how to walk through the steps. So here's the example. Sketch the graph of the equation y equals -1/2 x plus 7/2. Now, just like the example we just completed, we can easily and quickly see the y-intercept. That's just going to be b equals 7/2. So I can go to the y-axis and plot that y-intercept first. That's going to be at the point 0, 7/2. Done. Now, we see that the slope is negative. It's -1/2, or -1/2. That means for every 2 units we move to the right, we must move down 1 unit. And we have to go down because we can think of that numerator as -1. And if we do this, we move 2 to the right and 1 down, starting at the y-intercept of 0, 7/2, then we're going to be at the point 2, 7/2 minus 1, which is the same as the point 2, 5/2. Now I can plot that point. I already had the y-intercept plotted. I simply connect the dots, draw the line that goes through those 2 points, and that will be exactly the line that we wanted when we started this example. Now, notice that this line definitely has negative slope, and it's definitely pretty flat as well. Once I've drawn it, I can see this, and with a slope of -1/2, that's exactly what we would expect. So we've got some good critical thinking going here. We know that we needed a line that went down as we read from left to right because that slope was negative, and it needed to be kind of flat because the slope was pretty small. So it looks like we've drawn the right graph, and I would suggest then that we move on. Okay? All right, here's another example along these lines, and I'd like you to try this one first on your own to see how you do. So here's the example. I want you to sketch the graph of the line that's given by the equation y equals -2. All right, as you look at this problem, you might react pretty quickly with some sort of comment like, hey, wait a minute, there's no x term in that equation. Did he mess up somehow? Is there a typo? Is something wrong? The answer to all those questions is no, there's no typo, and there's nothing wrong. Everything's fine. In fact, you could even think of that equation this way. You could write it as y equals 0x minus 2, if you really wanted to, and then there would be an x term, but you would see that the slope is 0. In fact, we didn't need that 0x term there at all. The slope would have been 0 anyway. And what that means is that the line must be flat or horizontal if we want to use the fancier language. So y equals -2 is a pretty straightforward equation. It's the equation of a horizontal line with a y-intercept at -2. So if you just go to the y-axis, go down 2 units from the origin, you'll be at the point 0, -2, and through that point, you just have to draw a horizontal line. Once you've done that, you've actually sketched the graph of the horizontal line that we wanted in this example. Now, I'd like to transition a bit to sketching graphs that are still lines, but the equations are much more complicated. So let's do this together. It looks like we're doing some very different problems here. In fact, we're still drawing lines. It's just that the equations are a bit more complicated. If you're feeling pretty good about this right now, why don't you go ahead and try this one on your own, and then I'll come back in a moment and walk through the steps. So here's the example. Graph the equation y minus 6 equals 1/2 times the quantity x minus 3. Now, notice that that is the equation of a line. Do you remember what kind of form it's in? That's right, it's in point-slope form. It's very important that you actually see that equation in that way so that you can interpret the information that's being given to you in the equation. So, first things first, we look at that equation and we see that it's in point-slope form. Let's now pull out the information from the equation. First, what is the slope of this line? Well, the answer is the 1/2 that's sitting right on the right-hand side of the equation. So I know that my slope is 1/2. Now, what else do I know from the equation? What else can I pull out from it? Well, I know the coordinates of a point through which the line goes. And that point is 3, 6. Now again, I mentioned this in a previous lesson. Don't fall into the trap of saying that the point that it goes through is 6, 3. That would be the opposite of what you really want to write down. The 3 is in with the x, and the 6 is with the y. So the point that this line goes through is 3, 6. Now, it turns out with these two pieces of information, we can sketch our graph. We need to do a little bit more work, but not much. We first know that the graph goes through 3, 6. So we could just go right to some graph paper right now, to a set of axes, and plot 3, 6. We'd be done with our first step. After that, we know that the slope, which we often call the rise over run, is 1/2. So for every 1 unit that I go up, I need to move over 2 units to the right. So another point on the line is 5, 7. Where do the 5 and 7 come from? Well, 3 plus 2 is 5, and 6 plus 1 is 7. I plot that point now, 5, 7, and I now have 2 points plotted. I simply connect the dots, and I'm done. Now, notice something about the y-intercept of the graph. Once you've drawn the graph, it looks like the y-intercept is 4.5 or so. You could have determined that using that point-slope form of the equation if you wanted to go ahead and rewrite that equation. You should also notice that the x-intercept appears to occur somewhere around -9, 0. Again, you could check this as well by plugging that information into the equation, if you wanted. And lastly, we should really ask, does the graph make sense? Well, it definitely goes through the point 3, 6. We knew that it needed to do that. And it definitely has positive but smallish slope. The graph is definitely going up, not down, as we look at it and as we read it from left to right, but it's definitely not very steep. If the slope had been something like 20 instead of just 1/2, then we would have seen a line that would have much steeper slope, and the graph would have been much sharper as we read it from left to right. In this case, the graph is pretty flat, and so we're happy with our picture. Now, let's keep talking about graphs of lines. Let's look at another example of this type. And again, I ask you, can you graph this one before I actually walk through the steps? Here we go. The example is this. Graph the line which corresponds to the equation y minus 4 equals the quantity x plus 2 all multiplied by 7. Or you might say it this way, y minus 4 equals 7 times x plus 2. Again, I see immediately that this is in point-slope form. It's extremely important that we see that, because if you just see the equation and you don't recognize it as point-slope form of the equation of a line, then you won't know what the 4 is doing, or what the 7 is doing, or what the 2 is doing. So Once we have that, let's now interpret some information that the equation is basically trying to give us. First, the slope. Well, that's sticking out in front on the right-hand side of the equation. That's m equals 7. So that's positive, and 7 is relatively large. It's certainly a lot larger than 1/2. So I'm going to expect that the line I'm about to draw will go up as I read from left to right, and it's also going to be much steeper. It's going to go up much quicker than the line that we just drew in that previous example. So that's one thing we need to see. That's one bit of interpretation. Now, what else do I know? Well, I know a point that the line goes through. Now, if you said that it was 2, 4, you'd be close to the right answer, but that's actually not exactly right. And if you use 2, 4 as the point that the line goes through, then your graph is going to be wrong. So why isn't the line going through the point 2, 4? Well, it's because of that plus sign in the original equation. Remember, the point-slope form of the equation of a line is y minus y1 equals m times x minus x1. It's not y minus y1 equals m times x plus x1. You see the difference of the signs there inside the parentheses? The correct equation has a minus sign in it. Our equation has a plus sign in it. So what do? Are we just sort of stuck? Do we not know what to do? Nah, we're not stuck. We know exactly what to do. We just have to rewrite the equation that we started with just a bit so that it looks right in the point-slope form of the equation of a line. We started with y minus 4 equals 7 times the quantity x plus 2. I can rewrite that just slightly in the following way. Y minus 4 equals 7 times the quantity x minus negative 2. Notice the minus with the negative 2 would really be written as a plus 2 when we were normally writing this equation down. But I'm going to rewrite it this way with an x minus a negative 2 so that I really have the point-slope form of the equation of a line as it's usually written. And now that I've written my equation this way, I can see that the point that the line goes through isn't 2, 4, it's actually negative 2, 4. And that's a very important difference. That's going to change where I draw this graph once I get the correct point on the page. So now I can sketch my graph. I know two very important things. I know that the line goes through the point negative 2, 4, and I also know that it has slope 7. So I need to figure out another point that the line goes through. Starting at negative 2, 4, I could add 1 to the negative 2 and add 7 to the 4. Remember, the slope is 7, so it's 7 over 1. That's 7 in the y direction and 1 in the x direction. So I'm going to add 7 to the 4, and I'm going to add 1 to the negative 2. And when I do that, I know a second point that the line goes through. It's going to go through negative 1, which is coming from negative 2 plus 1, comma 11, and the 11 is coming from 4 plus 7. So it's very important that we interpret that slope correctly. That 7 is the same as 7 over 1, 7 for the rise, 1 for the run, and that means the 7 gets added to the y and the 1 gets added to the x. So I've got a line that goes through 2 points, negative 2, 4 and negative 1, 11. I plot those 2 points on my coordinates, on my coordinate axes, and once I've done that, I can connect those two and I'm done. And again, if you look at that line, it should have been pretty steep reading from left to right, and it should go up because my slope was positive 7. Now, if you've been following along pretty well, you should have a pretty good idea of what the graph of a straight line looks like once you've been given the equation. We've spent several minutes now working through those kinds of problems. Here's the equation, draw the graph. Here's another equation, draw another graph. Right now I think it's time to quiz yourself and see how you do. So here's what I'd like to try. Let's match the following equations to their graphs. So we're going to look at 4 equations now. All 4 of these are equations of lines, and I want you to match their graphs to the equations. So here are the 4 equations. X equals 3, y equals x minus 3, y equals 3, and y equals negative x plus 3. Now, let's walk through and see where those 4 equations match up to the 4 graphs that you see. Okay, now let's walk through those one at a time. First of all, x equals 3. What kind of a line do we get when we just have x equals a number? Well, in that case, you're actually going to have a vertical line, because if you think about it, all of the points that we go through have to have x equal to 3. So you might be at 3, 0, or 3, 1, or 3, 2. All of those points line up one above the other. And if you connect those dots, you're going to have a vertical line. So the first equation, x equals 3, must match up with a vertical line that you see on your screen going through the point 3, 0, for example. Now, what about y equals x minus 3? Okay, that is in slope-intercept form. You might not see the slope there, but it's really there. It's hiding a bit. It's right in front of the x. It's a 1. Y equals x minus 3 is the same as y equals 1x minus 3. Now, if you think about it for a moment, the y-intercept must be at negative 3, so I'm on the y-axis 3 units below the origin, and the slope is positive 1, which means the graph must be going in the positive direction as we read from left to right. Can you match that one up with one of the graphs? Great. Now the third equation, y equals 3. We've already seen an example of y equals a number. You remember what kind of equation that is? It's a horizontal line. So the graph of y equals 3 must be the horizontal line that's going through the y-intercept at 3. Well, lastly, whatever's left must be the right graph, but let's talk through it really quickly. The last equation was y equals negative x plus 3. Negative x is the same as negative 1x. So this is a line whose slope-intercept form we already have. The slope is negative 1, and the y-intercept is at plus 3. So its y-intercept must be above the origin, 3 units above, and the slope is now negative. So the line must be going downwards as we read it from left to right. And that should be the last graph that you had left. Now, if you got those right, fabulous. If not, you might want to do a little bit of review on graphing these lines that we've done in this lesson before you go on. But keep working at it. It'll come. It's a very important task to learn how to draw the graphs of straight lines given their equations. Okay, we've spent a good bit of time graphing lines. Now I'd like to switch to the other goal of this lesson, which is to talk about different ways that you can take a graph and manipulate it with shifting either left or right or up or down, or even flipping it around in order to get a new graph. So let me start with a graph that we're going to see a lot in this course. It's the graph of y equals x squared. Now we're going to talk a lot about where this graph comes from in future lessons. But for now, just trust me, this really is the graph of the equation y equals x squared. Sort of a nice U shape going right through the origin. Now, I'd like to use that graph to demonstrate some of the ways that we can move it and show how the algebraic equations change as you do that moving. So for example, let's say I wanted to move the graph of y equals x squared over 3 units to the right. Then I would get the graph that you see here. But what does the equation then look like once you've moved the graph? Obviously, the equation can no longer be y equals x squared because that graph went through the origin. This graph doesn't. It turns out that the new equation for this new graph is y equals the quantity x minus 3 whole thing squared. And all we've done is changed from an x being squared to an x minus 3 being squared. Okay, let's try something very similar. What would the graph of y equals x plus 4 squared look like? Well, if you start again with the graph of y equals x squared, the one we started with a few moments ago, and now move it 4 units to the left, then you would have the graph of y equals x plus 4 whole thing squared. And this leads us to the first of our graph changing rules, if you will. If you take the graph of a certain equation and change all the x's to x minus a number, you pick the number, then it turns out that you move the whole graph over that many units. If the number that you subtract, let's say x minus a, is positive, if that a is positive, then you move to the right. If the value of a is negative, then you move to the left. It's that simple. And that's how you go from something like x squared to x minus 3 squared or x plus 4 squared. Okay, that's how we move left to right when we're drawing our graphs. What next? Well, let me go back to y equals x squared again. This time I'd really like to move it up 2 units. What would I have to do to the equation to be able to get the graph to move up 2 units? Well, it turns out that that new equation would be y equals x squared plus 2. Remember, I wanted to go up 2 units. Notice that the x term was not affected this time. I left the x squared part alone. I actually added 2 to the whole right-hand side, if you want to think of it that way. So if I want to move a graph up by b units, let's say, we just have to add the amount b to the whole right side of the equation. We don't mess with the x so much, we just add that value of b to the right-hand side. And if b was a negative number, when I add that part, then the graph would actually go down instead. So for example, if I started with the graph of x squared and wanted to shift it down 3 units, the new equation would be y equals x squared minus 3. Now, as I move on to other rules for changing these graphs, let me also talk about how you could flip the graph of an equation, not just move it from side to side. We know how to move to the right and to the left by adding or subtracting an amount just to the x, but I also know how to actually flip over the x-axis. And it turns out that it's not that hard to alter the function in order to do that. If you multiply the whole right-hand side of an equation by -1, then it turns out that the graph that you started with will actually flip over the x-axis. So, for example, if I start with y equals x squared, which has this nice parabola going through the origin, nice U shape pointing up, and I switch that to y equals negative x squared, so I multiplied that right-hand side by -1, then it turns out that the graph switches from the nice U shape going up to, again, the same U shape, but now going down. Notice that it's still going through the origin. It just looks like it's been taken and flipped over the x-axis. And so flipping that way actually turns out to be done by multiplying the equation that you started with by -1. Now you have to multiply the whole right-hand side of the equation by -1 in order to flip that graph. But you can do this now to a wide variety of graphs and their equations simply by multiplying by -1. So, for example, earlier we talked about the graph of the line whose equation was y equals 5x minus 7. It goes through -7 on the y-axis, and it has a slope of 5, so it's somewhat positive and steep. If I wanted to then look at the graph of y equals negative the quantity 5x minus 7, which of course is the same as y equals negative 5x plus 7, then all I have to do is take the line we started with a moment ago and flip it across the x-axis. And immediately I would have the graph of y equals negative 5x plus 7 because that's the same as y equals the negative of the quantity 5x minus 7. Now, notice that the x-intercept of this line is the same as the x-intercept of the other line that we started with. It's just that the lines have been flipped around the x-axis. That's all we've done. We went from the line that had positive 5 as its slope and had a certain x-intercept, and we kept that intercept there on the x-axis and flipped the whole line across. So the y-intercept changed, but the x-intercept actually stayed the same. Now, next time I want to spend a little more time talking about what a function is. It's very important as we walk through this course to understand what a function is and to talk about several vocabulary terms that are related to functions. This would include things like what a domain of a function is, what the range of a function is. In fact, we don't even know yet what a function is. You and I will need to talk about that. And we'll want to understand which equations that we can write down are going to be functions. Turns out that all of the equations that you and I have walked through together in all of our lessons have been functions. It's just that I've been hiding that word from you all this time. But we want to talk about what a function really is and what its domain is and what its range is. And functions are going to play a very important role throughout the rest of this course. Believe it or not, functions play a very important role in things like precalculus and even calculus. So I really want to make sure that we've nailed down this concept of a function before we work into the rest of our course. I'm really looking forward to talking about those with you in the next lesson. In this lesson, we're going to transition to a very different topic than the topics that we've already seen in this course. And this is a topic that's extremely important throughout mathematics, not only in algebra, but in trigonometry, precalculus, and even beyond. It's the idea that we call a function. So let's start, as lots of mathematicians like to do, with a definition. So here it is. A function is a set of pairs of input values and output values in which each input value is assigned exactly one output value. The set of input values is called the domain of the function, and the set of output values, or things that come out of the function, are called the range of the function. So we have a function, which is defined to be a set of pairs, inputs and outputs. We have the domain, which is the set of inputs, and we have the range, which is the set of outputs. We'll often use notation like f parenthesis x parenthesis, which I'm going to pronounce f of x, to specify a certain function. So, for example, if we write f of x equals 2x plus 3, we mean that for any input value x that we plug into the function f, the output value will come from the rule 2x plus 3. So if I plug 0 into this function for the x value, then the output value is going to be written as f of 0, which is 2 times 0 plus 3, because the rule was 2x plus 3. And if I take 2 times 0 plus 3, that's the same as just 0 plus 3, which is 3. So f of 0 would be 3. I could also plug in 4 for x, for example, and the 4 would be part of the domain of the function, and the output value would be f of 4, which is now 2 times 4 plus 3, which is, according to our order of operations, 8 plus 3, which is 11. So the 4 would be in the set that we called the domain, that's the input values, and the 11 would be a member of the set we called the range, the set of output values. Now, it would probably be helpful to talk about lots of examples of things that are functions and even things that are not functions, as well as domains and ranges. These are very new terms for many of you, I'm sure. And so I'd like to walk through several examples to talk about what a function is, what's not a function, and if I am looking at a function, what its domain and what its range is. So here's an example to try to keep us going in this line. Consider the equation f of x equals x squared, x to the second power. So here's my question. Is this a function? Well, I'm going to tell you right now that it is. Yes, it is. And the reason it is because, according to the definition of a function, for every input value that I plug in, x, I need to have a unique output value, in this case, x squared. So I'm going to have that definition satisfied by the rule f of x equals x squared. It really will work. And now let's just try plugging in several values for x. Those input values are from the domain. And let's see what the output values, or the range elements, look like. So for example, f of 0 is 0 raised to the second power, or 0 squared, and of course that's 0. So when I plug in 0, I get 0 back. That's perfectly legal to have the same input and output value. No problem there. When I plug in 1 to f, I would have f of 1. That's 1 squared, and 1 squared is 1 times 1, which is 1. Again, notice I had 1 as the input value and 1 as the output value. No problem. What's f of 2? Well, f of 2 is 2 squared, which is 2 times 2, which is 4. So the domain element 2, or input value 2, is connected to the output value 4, and that 4 is part of the range. And lastly, f of 3. When I plug 3 in, I have 3 squared, and 3 squared is 3 times 3, which is 9. So the input value 3 is connected to, if you will, the output value 9. There's no ambiguity as to what each output value is going to be. There's no confusion as to, well, if you plug that in, I'm not sure what's going to come back. Functions always know when you plug in a certain input value what the output value is going to be. There can't be any confusion or questioning whatsoever. Notice that I could have also plugged in some negative values. That would have been perfectly fine, so let's do that. What if I wanted f of negative 1? Well, that would be negative 1 squared. Now let's be careful. That's the same as negative 1 times negative 1, and the two negatives cancel each other, and you just get 1. So the input value negative 1 has an output value of 1. f of negative 2 is negative 2 squared, which is negative 2 times negative 2. And again, the negatives cancel with one another, and I just get positive 4 as the output value. Again, part of the range. That 4 is part of the range. And f of negative 3 would be negative 3 squared, which is negative 3, times negative 3, which is 9. All of this is perfectly fine. But I could hear a few of you saying something like, hey, wait a minute, time out. Notice that f of 2 and f of negative 2 were the same. They were the same output value. They were both positive 4. Is that okay? Do I still have a function if two different input values, 2 and negative 2, have the same output value of 4? The answer is yes. It's okay for a function to have two different input values connected to the same output value. What's not okay is to have the same input value going to two separate output values. That's bad when you're looking at functions. A function cannot have one input going to two separate output values. But that's not what f of x equals x squared is doing. It does have two inputs going to the same output. That's okay. That's perfectly fine. F of x equals x squared really is a function. Now, let's talk a bit about domain and range in this case. We saw a few numbers that go into each of those sets, but I'd really like to think about what the full domain and the full range looks like. So notice that you're actually allowed to plug in any real number that you want into f of x equals x squared. There's nothing about x squared that keeps us from plugging in any real number. We could have plugged in 19 or negative 103. We could have even gone crazy and plugged in pi or square root of 7. And that means that the domain of this function, the set of all input values that we can plug in, is actually the whole set of real numbers. And if you want to think of it as a real number line, that's fine as well. We would denote that domain with an open parenthesis, minus infinity to infinity, and then end that with a parenthesis as well. That means that we're going to include all of the real numbers in the domain. They're all legal input values, if you want to think of it that way. Now, what about the range? Okay, the range is the set of output values that are going to come out of the function. Well, the range in this case is a little different. Notice that you're never going to have a negative number as an output value of this function, because the output values are all squares, right? Even when you plug in a negative number into the function, did you notice you get positive numbers back? When we plugged in negative 2 as an input, we got positive 4 back as an output. So what's the smallest output that you can get from this function? Well, the answer is actually 0. And that happens when you plug in 0 for x. F of 0 is 0 squared, which equals 0. All of the other outputs are going to be greater than 0. Just like when you did f of 1, we got 1. F of 2 was 4. F of 3 was 9. So the range in this example is not the set of all real numbers. The range is just the set of non-negative real numbers, or the interval from 0 to positive infinity, including the 0. That means I'm going to denote the range here as the following. I'm going to put a square bracket, 0, comma, infinity, and then close with a parenthesis. The square bracket next to the 0 tells me that 0 is included in the set. So it's included in the range. Infinity is not a real number, so I'm not going to put a square bracket next to the infinity. I'm just going to put a parenthesis. So the domain in this problem was minus infinity to infinity. That's the set of all real numbers. But the range is just square bracket 0 to infinity. It's just basically half of the set of real numbers if you want to think of it that way. It's all of them from 0 on to plus infinity. All right, let's look at another example now of a function and even talk about its domain and its range. I want us to think about this function. F of x equals 4x plus 2. Now, I'm hopeful that for some of you, you're thinking, hey, that looks a lot like y equals 4x plus 2. And we already know what that is. That's the equation of a straight line. Well, the same is true for f of x equals 4x plus 2. It's just a function whose graph is a straight line. So what we've learned about lines already in this course helps us to understand this example. Now, let's talk about its domain and its range. Well, there aren't any numbers that we can't plug in for x. Everything you want to plug in for x that comes out of the set of real numbers is perfectly fine. So the domain is the set minus infinity to infinity. It's the set of all real numbers. What about the range? Well, turns out that the range, which again is the set of output values that's going to come from the function, is going to cover every possible y value you can imagine if you want to think about it on the y-axis. So the graph, remember, it's just a straight line. The graph is actually going to go from minus infinity in the y direction all the way up to plus infinity in the y direction as well. And that means that the graph tells me what the range of this function is going to be. It's going to be the interval, again, from minus infinity to infinity. So here's an example where the domain and the range are actually the same set of numbers. Now, let's look at another example. Take this function, f of x equals square root of the quantity x minus 3. Now, believe me, it's a function, but I'd really like to think about this one in terms of domain and range. So let's talk about those as we work through. Let's start with the domain. Remember that the domain is the set of input values that we're allowed to plug in. Now let me ask you a question. Can you and I ever compute square root of -5? Well, the answer is no. What about the square root of -9? The answer is again no. Notice that square root of -9 is not the same as -3. Some students fall into that trap. It's very tempting to say that the square root of -9 is -3. But the square root of -9 cannot be -3 because -3 times -3 is +9, not -9. So the square root of -9 as a real number doesn't make any sense at all. In fact, square root of x minus 3 as a function can only be computed if the x minus 3 part is greater than or equal to 0. And that's the same as saying that the x has to be greater than or equal to 3. Well, guess what? You and I just figured out the domain of this function. It's got to be all the numbers starting at 3 and going to plus infinity. And the way we denote that is square bracket 3, comma, infinity, and again, a parenthesis next to the infinity because infinity is not a real number. Now, what about the range of the function? The range is trying to tell me what happens with the y values or the output values of the function. Well, you and I both know that the square root of anything is always going to be either 0 or positive. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and so on. What does that mean about the range? It means that the range is the set of all numbers from 0 to plus infinity. And I can write that as an interval, bracket 0, comma, infinity. Now, let's look at one last example about these domains and ranges really quickly. Let's think about f of x equals x divided by the quantity x minus 2. So I have x on top divided by x minus 2. Now we're going to talk about these kinds of functions later in the course where we have a piece on top divided by a piece on the bottom, x divided by x minus 2. But I want to think about this example today just in terms of domains and ranges. So here's my question. What values would give us a problem to plug into a function like x over x minus 2? Well, there's no problem with the x in the numerator. I'm allowed to plug in anything I want there. But the denominator might actually cause me a bit of trouble because of division by 0. You and I both know that we can't ever divide by 0. Notice that if we try to plug in x equals 2, we will have a problem because f of 2 equals 2 divided by 2 minus 2, which is 2 over 0. That's not defined. We can't have a 0 in the denominator. And therefore, x equals 2 cannot be in the domain of my function. I cannot plug 2 in. Notice though, I can plug anything else in that I want as long as I avoid 2. So it turns out the domain here is the set of all real numbers x not equal to 2. I just have to pluck the 2 out and throw it away. I can keep all the other real numbers. That will be my domain. All right, we've talked enough about domains and ranges for now. I'd like to say a few words about some more terms that we have with functions, and then I want us to talk about how to combine functions using addition, subtraction, and so on to get new functions. Okay? So throughout the course, we're going to talk about some different notations for functions. Things like f of x equals x plus 1. I could also call it g of x equals x plus 1. I could have called it y equals x plus 1. I might even have things like h of t equals t plus 1, and things like that. The names of the functions and even the variables aren't the important thing here. What's important is that we know what the input value is and what the output values are. So in an equation like y equals x plus 1, we normally think of the x as the input and the y as the output. Or to use some fancier language, we think of the x as the independent variable and the y as the dependent variable. That input variable doesn't depend on anything else, but the output variable always depends on what you plug in. So that's why we're calling the input the independent variable, and the output we're calling the dependent variable. We won't use this language too much, but we will use it every once in a while, and you'll find it in lots of other textbooks too. So I wanted to make sure we hit on it before we moved on. Now, let's talk about how you can combine functions using different operations just to make sure we know how to build bigger and bigger functions out of smaller and smaller functions. So you already know about things like addition and subtraction and multiplication and division from just doing arithmetic. Well, it turns out you can do the same sorts of things with functions. So let's look at a couple quick examples. First of all, let f of x equals 5x plus 4 and let g of x equal 2x minus 10. Can you find f plus g and f minus g? If you want to try, stop the video at this time. Okay, let's try to do these together now. F plus g and f minus g. First of all, just so you know, f plus g is a new function. And f minus g is also a new function, which uses the f and the g and puts them together. So we're going to build new functions out of old ones. First, f plus g. It's exactly what you think it is. You just take the 5x plus 4 plus 2x minus 10. And when you add those together, you're going to have 5x plus 2x plus 4 minus 10, which is 7x minus 6. It's a new function, 7x minus 6. What about f minus g? Well, now you got to be a little more careful. It's going to be 5x plus 4 minus the quantity 2x minus 10. And now that minus sign that's sort of in the middle needs to be distributed into that second set of parentheses. And you'll have 5x plus 4 minus 2x plus 10, because minus times minus gives you a plus, and that's the same as 5x minus 2x plus 4 plus 10, which is 3x plus 14. Don't lose that minus sign. It's got to be distributed as you go through. Now, let's try something a bit harder. I'd like to try to find the product of two functions very, very quickly. Remember, product just means multiplication. So let's try that here. Let f of x equal 5x and let g of x equal x plus 4. Let's find f times g, which is the product of f and g. Well, f times g is exactly what you think it is. You just have to multiply the two terms together. And f times g is going to be 5x times the quantity x plus 4. So I have to distribute that 5x in, and I'm going to have 5x times x plus 5x times 4, which is 5x squared plus 20x. Now notice, we started with two linear functions. 5x and x plus 4 are both going to give you lines if you draw their graphs. But we now created something that's not linear because it's got an x squared in it. Really cool. So you can actually start with two linear functions, multiply them together to get something totally different. Now, what would f divided by g look like? Well, f divided by g would just be 5x on top divided by x plus 4. And unfortunately, there's nothing else you can do with that to make it any cleaner or more simple. So we just leave it that way. It's still a very interesting function though, because now it even has problems with its domain. Notice you've got to avoid division by 0 at that point. So even f divided by g is a new function, and it's got some interesting properties as well. Now, in this lesson, I'd also like to talk about an operation which you may or may not have seen before, and it's a very important operation in building new functions, especially as you go on to higher and higher mathematics. It's called composition. In a nutshell, if you want to compose two functions, it's like plugging one of the functions into the other function. So it's not multiplying them together, it's actually taking one of the functions and plugging it into the other. So let me show you an example. Let f of x equal 2x plus 4 and g of x equal 3x plus 2. I want to find the composition of f and g. Now, to do this, let's talk about a bit of notation first. The composition of f and g is going to be denoted as f of g of x. Now, notice how it looks like we actually plugged g right into f. It's like we forced it in. That notation is trying to tell us what we really want to do. We want to take the rule for g, which is the quantity 3x plus 2, and we want to plug that in for f. We want to plug that in for x in the rule for f of x. So I'm going to take the 3x plus 2 and I'm going to plug it in for x everywhere I see x in the rule for f. And this is what we would have. f of g of x would equal 2 times 3x plus 2 plus 4. Do you see how I took the 3x plus 2 and actually put it into the role of the x inside f of x? And once I've done that, I can actually simplify. So f of g of x would be 2 times 3x plus 2 plus 4. I distribute that 2 to give me 6x plus 4 plus another 4, and that gives me 6x plus 8. So f of g of x in this case is 6x plus 8. Now, there's something cooler you can do here. You can also find g of f of x as well. Now, let me suggest you try that yourself. Remember, you're just plugging in all of the function f into the x part of the function g. You're actually plugging them right in. So, let's try that. All right, let's do it together now. If we want g of f of x, it's going to be 3 times 2x plus 4 plus 2. So I've taken the 2x plus 4 and plugged it in for x inside the rule for the function g. So I have 3 times 2x plus 4 plus 2, which is 6x plus 12 plus 2, which is 6x plus 14. Now, let's do a bit of critical thinking together. I want you to look at something. Look at f of g of x and look at g of f of x. They're both functions. They look kind of similar, but notice that they're different. They're actually two different functions. Most of the time, almost all of the time in fact, f of g of x is not going to equal g of f of x. Sometimes they're equal, and that's going to tell us something very special about f and g. They have a special relationship when f of g of x equals g of f of x. But I'm going to save that topic for another day. We'll see that idea of f of g equaling g of f later on. Maybe even if you take a precalculus class, you might see that more and more. But most of the time, f of g will not equal g of f. All right, let's look at one more composition problem just to make sure we've got it down. See if you can do the following composition. Let f of x equal x squared and g of x equal x minus 7. I want you to find f of g of x and g of f of x. Okay, what answers did you come up with? Well, let's start with f of g of x. I'm now going to take g of x and plug it in to f, and when I do that, I'm going to have x minus 7 squared. And there's nothing really more to do. If you'd like to expand it, you're welcome to do it, but actually, you can just stay with x minus 7, the whole thing squared. All right, now let's do g of f of x. So now I'm going to take the rule for f of x and plug it into g. So I'm going to replace all the x's in the g function with whatever the rule for f of x is. In that case, it's x squared. So g of f of x is x squared minus 7. There's nothing else to do. It's just x squared minus 7. Now, here's a question. In this example, is f of g of x equal to g of f of x for every value of x? So let's plug in x equals 8 into both functions and see what we get. F of g of 8 equals 8 minus 7 squared, which is 1 squared, which is 1. While g of f of 8 equals 8 squared minus 7, which is 64 minus 7, which is 57. Notice that these two output values are different. So f of g of x is not equal to g of f of x in this case. All right, we've spent some time talking about new terminology related to functions. We've discussed some of the operations that can be used to build new functions out of old functions. I'd like to close this lesson with a visual idea again for how we can tell whether a specific graph is the graph of a function. I'm not going to worry so much now about the rule for the function or its domain or range. I just want to know, if you hand me a graph, can I tell quickly whether it's the graph of a function? And this test is going to be called the vertical line test. Here's how it works. If you can draw a vertical line that crosses through at least 2 points on a graph, then we know that that graph does not represent a function. So let me repeat it. If you can draw a vertical line that crosses through at least 2 points on a graph, then that graph cannot be the graph of a function. So let me show you some examples. Let's start with the graph of a circle that's centered at the origin and has radius 2. It would look something like this. Now, all you need to do is be able to draw one vertical line through this graph. If that vertical line crosses more than 1 point, then this graph cannot be the graph of a function. Well, in the case of a circle, you've got all kinds of choices for where to put that vertical line. In fact, just take the y-axis as it's drawn right now, and you can see that the y-axis crosses a point at the top of the circle and a point at the bottom of the circle. As soon as that happens, it means that the circle is not the graph of a function. Okay, let's try another example. Let's take this graph, which looks a little bit like a sideways U, so to speak. And I want you to think about it for a second. Is this the graph of a function? Well, just like with the circle, I can draw a vertical line that crosses through this graph at 2 points. It's pretty straightforward, in fact, to see that the y-axis again crosses 2 points on the graph. But it doesn't always have to be the y-axis. As long as you can find one vertical line that crosses the graph at 2 or more points, then that graph cannot represent a function. So this sort of sideways U graph definitely does not represent a function. Okay, let's try instead something like y equals x squared. We saw in the previous lesson that the graph of y equals x squared looks like this nice U shape going through the origin and then going up. Here's my question. Function or not a function? According to the vertical line test, this is a function. Notice no matter where you put that vertical line, it's going to cross the graph in only one place. So by the vertical line test, this is the graph of a function. Well, in this lesson, we've talked a lot about functions. We've laid a lot of groundwork for lots of future conversations that we'll have about functions as well. We've talked about domains and ranges, and we've talked about this vertical line test, which is a visual way of seeing whether a graph is a function or not. Next time, we'll return to thinking about linear equations again, but this time we'll talk about systems of linear equations, two equations that are there together, and finding solutions for those systems. I look forward to talking with you then. In our previous lesson, we introduced the idea of a solution of a system of two linear equations, and we talked about one way to find such a solution. We called it graphing the two lines that correspond to the two equations in the system and looking for their intersection point. When we finished that lesson, I mentioned a few reasons why the method of solving by graphing is a bit weak, and I hinted that it would be nice to have some other ways to solve these systems. So in this lesson, we're going to talk about two such ways to solve the systems that don't need the visual or the graphical approach. They're going to be much more algebraic, and they have names. They're called the method of substitution and the method of elimination. So let's start by talking about the method of substitution. The method gets its name from the fact that you substitute information from one of the equations into the other equation and then solve this newly modified equation. The solution of that new equation is the solution of the system. So even though you're playing with the equations, changing them and making them look like new equations, it turns out that whatever you find for the solutions of those new equations is exactly the solutions that you wanted to the original system. So let's start with an example, a pretty straightforward example, and see how we use this method of substitution. Let's take the system 2x plus 3y equals 4 and negative 6x plus y equals negative 7. Now, I want you to notice that if you tried solving this system by graphing, like we had in the previous lesson, it would take a little bit of work. You'd have to change or rewrite these equations into something like slope-intercept form before you could easily sketch the graphs, and then you'd have to do some other work to look for that intersection point and so on. So instead of trying something like graphing, let's try solving this by what I'm calling substitution. So here's how. First, I'm going to add 6x, to both sides of the second equation, and it's going to give me a new equation. Y equals 6x minus 7. Now, in fact, I've now written that in slope-intercept form, but that's not my goal in doing that. The reason I've written that equation as y equals 6x minus 7 is that I now know that I can replace any y that I see with the quantity 6x minus 7. That's because y equals 6x minus 7. So I'm going to go back to the other equation in the original system, and anywhere I see a y, I'm going to substitute 6x minus 7. That's why we call this technique the method by substitution. And that other equation, instead of being 2x plus 3y equals 4, is now the same as 2x plus 3 times 6x minus 7 equals 4. I've substituted for y the quantity 6x minus 7. And now, if you look, there are no more y's in that equation. There's only one variable, and it's x. Now, it does appear a couple times, but there's just that one variable x. So if I can now solve that equation for x, I'll be halfway to finishing this problem. So let's look at this equation. 2x plus 3 times the quantity, 6x minus 7, equals 4. And let's start trying to solve that for x. The first thing I'm going to do is distribute that 3, and that's going to give me 2x plus 3 times 6x minus 3 times 7 equals 4. We have to distribute that 3 with the 6x and with the 7. And that means I have 2x plus 18x minus 21 equals 4. 2x and 18x added together gives me 20x, so I have 20x minus 21 equals 4. I can add 21 to both sides, and that gives me 20x equals 25. And if I divide both sides by the 20 to get the x by itself, I will have x equals 25 over 20, which is the same as 5/4. So I now know that x equals 5/4 is actually part of my solution of the system. That's great. Now I need to find the value for y. Well, I knew that y equals 6x minus 7. So if I plug in x equals 5/4 into that equation, I can get y. And namely, I'm going to have y equals 6 times 5/4 minus 7. Remember, x is 5/4. And that's the same as 3 times 5/2 minus 7, or 15/2 minus 7. And if I get a common denominator, that's the same as 15/2 minus 14/2. And of course, when you do that subtraction, you just get 1/2. And guess what? We now know the solution of our system, assuming we've done all the mathematics correctly. It's going to be x equals 5/4. I found that a few moments ago. And y equals 1/2. If we wrote that as an ordered pair to think about a point in the xy plane, it would be 5/4 comma 1/2. Now, as I mentioned earlier, it might have been kind of hard to see this point, 5/4 comma 1/2, if we had solved this by graphing. Even with graph paper, 5/4 and 1/2, neither of those are whole numbers. It would have been hard to see that. But I'd like to suggest that we get into a good habit of checking our solutions to these systems. Let's do that with the equations by plugging in x equals 5/4 and y equals 1/2 into each of the original equations. Let's do that quickly. We start with 2x plus 3y equals 4. Plugging in x equals 5/4 and y equals 1/2 gives me 2 times 5/4 plus 3 times 1/2 equals 4. That's the same as 5/2 plus 3/2 equals 4, or 8/2 equals 4, or 4 equals 4. That's correct, so that's good to go. Let's try the other of the original equations. Negative 6x plus y equals negative 7. Plugging in the information for x and y gives me negative 6 times 5/4 plus 1/2 for y equals negative 7. That's the same as negative 15/2 plus 1/2 equals negative 7, or negative 14/2 equals negative 7, or negative 7 equals negative 7. That's also true. So the solution worked for both of the original equations, and therefore I'm guaranteed, I'm certain, that x equals 5/4 and y equals 1/2 is the solution of that system. Now, I'd like to look at a second example of solving by substitution just to make sure we have it down. So let me suggest, if you'd like, that you try this one first on your own, if you want, and then we can check back together to see how you did. Solve the following system. 4x plus 2y equals 8, and y equals 2x plus 1. Okay, so what answer did you come up with? Well, let's solve it together and let's make sure that we got the same answer. Notice that the second equation in the original system already had one of the variables isolated or by itself. Notice that y equals 2x plus 1 was given to us. So we can just substitute 2x plus 1 in for y in the first equation and see what we get. So let's do that. That first equation was 4x plus 2y equals 8. I know that y has to be the same as 2x plus 1, so I'm going to put 2x plus 1 in for y, and it's going to give me 4x plus 2 times the quantity 2x plus 1 equals 8. And that's the same as 4x plus 2 equals 8. I just used the distributive property again. And that's the same as 8x plus 2 equals 8, or 8x equals 6 after I subtract a 2 from both sides. So x has to be 6 divided by 8, which is the same as 3/4. So we now know that our x value in the solution is 3/4. Well, what about the y value? We'll go back to the original equations again. We knew that y equals 2x plus 1. We now know that x has to be 3/4 in order to be the solution. So I'm just going to plug in 3/4 for x into the equation y equals 2x plus 1. And when I do that, I'll have y equals 2 times 3/4 plus 1. So y is 6/4 plus 1. And if I get a common denominator of 4, that's the same as saying y equals 6/4 plus 4/4. And that's the same as y equals 10/4 when you do the addition. And simplifying that fraction just a bit gives me y equals 5/2. So the solution of my original system is the point 3/4, 5/2. We can check this by plugging these values into the original equations and confirming that everything is correct. We could also just sketch the graphs of the two equations to see if the intersection point is 3/4, 5/2. Well, I'm going to suggest we try that graphical approach here instead of plugging in the numbers and checking everything. I always like to go visual if we can. And if you look at those graphs for just a second, you'll notice that there is an intersection point, and it appears that the x-coordinate is just less than 1, maybe like 3/4, which is what it's supposed to be, and the y-coordinate looks like it's somewhere between 2 and 3, kind of like 5/2, which is 2 and 1/2. And this gives us a good sense that we found the correct solution. Of course, if we wanted to be completely confident in the answer, we'd actually have to plug our numbers back into those equations to make sure everything worked. And if you want to do that, I think it would be a great idea to plug those numbers in just to make sure. Now, before I move on to the next example, let me point out again that using the method of graphing from the previous lesson, it may have been hard for us to see the exact solution. So this example again points out that the method of graphing, although it's nice, and if you're a visual learner, it's a really wonderful way to find those solutions. In this case, it can be very hard to find the exact solution unless the coordinates of that point are whole numbers. So I wouldn't mind if we use the method of graphing always, but it can be very hard to find the exact answer sometimes. And that's why something like the method of substitution is so great. Now, I'd like to transition to another example of solving a system of equations where even the method of substitution might not be the best way to go. So let me walk through the example and hint at why I think a different method might be better in this example. Here's the example. The system is 2x minus 5y equals 12 and 6x plus 5y equals 36. Now I want you to notice something. There doesn't appear to be a natural choice for what to do in order to use the method of substitution. You don't really have one of the variables isolated in either one of the equations. Neither of the equations has something like x or y completely by itself. And it looks like we're going to have to do a fair bit of work just to get one of those variables by itself. So, although that work is not impossible to do, what I just mentioned, I think, is some motivation for why we might want to look for another method for solving this system. And in this case, there is another method, and that's what I want to talk with you about for the remainder of today's lesson. It's called the method of elimination. So let me demonstrate the method by working through the system that I just showed you and pointing out the different steps in the method. So first, I want you to notice that if we added the two left-hand sides of the system that I gave you, you would have the following: 2x minus 5y plus 6x plus 5y. If you add those two together, the 2x plus the 6x gives you 8x, and the minus 5y plus the 5y gives you 0y. So you actually have 8x plus 0y, which is the same as 8x. Now, what significant thing just happened? Well, the y, the variable y, was completely eliminated. And this is where we get the name for this method, the method of elimination. If you add the full sets of equations now, both the left-hand sides and the right-hand sides, it turns out that what you'll be left with only has one variable because the y gets eliminated. So now, go back to the original set of equations and just add both the left-hand sides and the right-hand sides, and let's see what you get. Well, you have 2x minus 5y equals 12, and 6x plus 5y equals 36. We know that the sum of the left-hand sides of the equations is just 8x. We did that together a moment ago. And the 12 plus the 36 is 48. And so now you're left with a new equation. 8x equals 48. And that equation only has one variable. The y has been eliminated. You just have the x. So if I just take 8x equals 48 and do a little more algebra, I can actually find the x value, which is part of the solution of this system. It's really cool. So let's take that, 8x equals 48, and divide both sides by 8. On the left-hand side then, I'll just have 1x, or x, because the 8's will cancel. And on the right-hand side, I'll have 48 divided by 8, which of course is 6. So here's the point. That value, x equals 6, is actually part of the original system of equations. So we need to keep that in mind, x equals 6. I now need to find the y. Well, what do I do? Well, I know x equals 6, so I can go back to either of the original equations, plug in 6 for x, and solve for y. And it doesn't matter which of the two original equations you choose. I'm going to choose to go back to 2x minus 5y equals 12, and I'm going to plug in x equals 6. Let's see what I get. Well, I'm going to have 2 times 6 minus 5y equals 12, which is the same as 12 minus 5y equals 12. And now if I subtract 12 from both sides, I'll have negative 5y equals 0, or y equals 0. So the solution of the system appears to be 6, 0. Let's check. I've got 2x minus 5y equals 12. And if I plug in 6 for x and 0 for y, I'll then have 12 minus 0 on the left equals 12, or 12 equals 12. So that's true. Let's try the other equation now, which hasn't really played much of a role in this example. I have 6x plus 5y equals 36. I can plug 6 in for x and 0 in for y, and I'll have 6 times 6 plus 5 times 0 equals 36, which is the same as 36 plus 0, which is equal to 36. And of course, that's just 36 equals 36. That's also true. And that means we're done, that we really did have the right solution, x equals 6 and y equals 0. So that was good. That was the method of elimination. Now I want to try a second example that also uses that method to see if we've got the idea down. So let me suggest that you try this one first if you want, and then we'll get back together in just a moment. So here's the question. I want us to solve the following system by elimination. The system is 5s plus 4t equals 27, and 3s plus 4t equals 31. Now, let me give you a bit of a hint, just in case you weren't sure how to start that problem. I'm going to give you the hint that the t variable is the one to try to eliminate. Okay? Now, let me also point out before we move forward that the variables here are not x and y. They are s and t, but that is not a problem at all. It's just new names, and that's not going to be an issue for us. We just need to remember that one of the variables is s, the other one is t, so the solution is going to be some number for s and some number for t. Now, let's start the problem by trying just to add the two equations together. In fact, that's what I did in the previous example, so let's just add them both together and see what we get. When I do that, I'm going to have 8s plus 8t equals 58. Now, what happened? Or maybe I should ask it this way, what didn't happen? Well, what didn't happen is that neither of the two variables got eliminated. You still have some s and you still have some t floating around in the equation. That's a sign that what we did didn't really help us. Now, what we did was legal, it was mathematically correct, but it didn't help us at all. So we should try something other than adding the two equations together to see if we can eliminate a variable. And if you look at those original equations again, you realize that if you can subtract one of the equations from the other, then the t's will be eliminated. So I'm going to subtract the second equation from the first. Let me think of it this way. Let's multiply the second equation by -1, and then let's add. If you multiply the second equation by -1, then that equation becomes -3s minus 4t equals -31. And if you add that to the original first equation, 5s plus 4t equals 27, you're left with 2s equals -4. Notice that by adding the 4t and the -4t, we've eliminated the t. You're down now to just the variable s, and so you can solve that for s. Now, before we move on though, let me point something out. There's a common mistake that students often make when they have to multiply by -1 throughout one of the equations, as I just did a moment ago. You have to make sure you distribute that -1 throughout the equation. So make sure that all of the signs become negative. In particular, I needed a -4t in order to get that eliminated. Now, once that t's been eliminated and I have 2s equals -4, I can just divide both sides by 2, and I'll have s equals -2. But of course, we're not done yet, because in order to find the solution of this system, I need a value for s and I need a value for t. All I have right now is s equals -2. But if I just go back to one of the original equations and plug in s equals -2, I can solve for t. In this case, I'm just going to choose the second of the original equations and plug in s equals -2, and that'll allow me to find t. So let's do that here. We have 3s plus 4t equals 31. With s equal to -2, I need 3 times -2 plus 4t equals 31. So -6 plus 4t equals 31. Adding 6 to both sides gives me 4t equals 37. So t equals 37 divided by 4. And that means our solution is s equals -2 and t equals 37 over 4. Now, if you want to write that as an ordered pair, you can, just as -2 comma 37 over 4. But the key now is that you have to remember which one of those was s and which one of them was t, because we're no longer using the variables x and y. But as long as you keep that straight, s equals -2 and t equals 37 over 4, you can actually write the solution as an ordered pair. And let me just point out again, at the risk of sounding like I'm really down on the method of graphing, I hope you realize that if you tried to draw the graphs of these two lines and spot the point -2 comma 37 over 4, that would have been really hard to do. I would have given you 2 gold stars if you could actually see 37 over 4 exactly. So let's, before we move on to another example, just make sure that -2 comma 37 over 4 really is our solution, and then we'll keep going. How do we check that it really is? We go back to the original equations, plug in -2 for s and 37 over 4 for t. Here we go. 5s plus 4t equals 27. That means 5 times -2 plus 4 times 37 over 4 needs to equal that 27. That gives me -10 plus 37, because those 4's are going to cancel each other. And -10 plus 37 is 27. 27 does equal 27. That checks. Now let's try the second equation. 3s plus 4t equals 31. Plugging in -2 for s and 37 over 4 for t gives me 3 times -2 plus 4 times 37 over 4 equals 31. The left-hand side is just -6 plus 37, which is 31. And so those two values really make both equations work, or make both of them true. So indeed, I really do have a correct solution. Now, let's look at another example which appears, at least at the beginning, to cause us some trouble, but I don't think it really does. It's going to take a little more work, and if you're feeling pretty confident that you might be able to see what that work is, I want you to try stopping the video and trying it yourself. Let me give it to you first, and then we can do it together in just a moment. Solve the following system. -2x plus 15y equals -32, and 7x minus 5y equals 17. Okay, let's try this thing together now, especially if you didn't see exactly how to get started. Let's just start somewhat carelessly, if you want, by just adding the two equations together. Let's just see what happens. If you add the two equations together, you get 5x plus 10y equals negative 15. Well, x is still there and y is still there, so we didn't eliminate one of the variables, so that doesn't help us much at all. Okay, we've tried adding. Let's try subtraction. We did that earlier. Let's try subtracting the two equations, and if you do that, you get negative 9x plus 20y equals negative 49. Remember, you've got to distribute that minus sign throughout in order to do this correctly. But notice, the x is still there and the y is still there. Ugh, so this elimination doesn't look like it's helping. But it turns out that there's something else we can do in order to make the elimination work. We are allowed to multiply either of our equations on both sides by any constant that we choose. So we can just multiply, we've multiplied by negative 1 a couple times, but we can actually multiply by other numbers as well. And in this case, let's try multiplying the second equation by the number 3. Okay? You might have had that idea already, and if you did, that's fabulous. Let's try it together here. Take that second equation and multiply it by 3, and you'll get 21x minus 15y equals 51. And if you write that with the first original equation, negative 2x plus 15y equals negative 32, do you see what you might try? Let's try adding. If you add these two equations now, the y variable will be eliminated. So let's add them and let's see what we get. Well, the left-hand side is going to become 19x plus 0y, which is just the same as 19x, and the right-hand side becomes 19. And the huge thing that just happened is that the y variable was eliminated. You can now divide both sides by 19, and you just get x equals 1. And that means you're halfway home to the solution of this system. You can now plug in the 1 into either of the original equations and solve for y. Let me go back to negative 2x plus 15y equals negative 32 and plug in x equals 1. In that case, I'm going to have negative 2 times 1 plus 15y equals negative 32. That's the same as negative 2 plus 15y equals negative 32. Adding 2 to both sides gives me 15y equals negative 30. Dividing both sides by 15 gives me y equals negative 2. And that means my final solution, as long as I've done everything right, is 1 comma negative 2, or x equals 1, y equals negative 2. Let's plug the information in just to make sure that we've done everything correctly. You should always do these checks. So we go back to the original equations and plug in 1 for x and negative 2 for y. The first equation is going to then be negative 2 times 1 plus 15 times negative 2 equals negative 32. That's the same as negative 2 minus 30 equals negative 32, which is negative 32 equals negative 32, and that's correct. So that's good. Now let's try the other equation. 7x minus 5y equals 17. Plugging in 1 and negative 2 for x and y respectively gives me 7 times 1 minus 5 times negative 2 equals 17. That's the same as 7 minus a negative 10 equals 17. And those two minuses cancel each other, if you will, or turn into a plus, and you get 7 plus 10 equals 17, or 17 equals 17. And since we've made both of those equations true, we know that x equals 1 and y equals negative 2 really is the solution of the original system of equations. Well, we've talked in this lesson about two new methods for solving systems of linear equations. One was called the method of substitution, and the other was called the method of elimination. They both feel a lot like algebra, where we manipulate the symbols in the equations to get to our answers. They're much less visual or graphical compared to the method of graphing that we saw in a previous lesson. In our next lesson, I'd like to think some more about these methods, but I want to take the problems one step further. I want to talk about solving systems of 3 equations with 3 variables or 3 unknowns. It turns out that these problems aren't much harder than what you and I just did, but they do require a bit more work. And I look forward to talking about that in our next lesson. In the last couple lessons, we've talked quite a bit about solving systems of linear equations, spending most of our time on systems with 2 linear equations and 2 unknowns or variables. In this lesson, I'd like us to push further with this idea by considering systems of linear equations with 3 unknowns. So we'll have 3 equations and 3 variables. We definitely don't want to solve these kinds of systems by graphing. I've talked about that in a previous lesson, but we can certainly use the method of elimination in a smart way to find the solution of a system with 3 linear equations. So in this lesson, I want to talk through as many examples as we can, so let's get right to it with the following example. I want us to solve this system of 3 linear equations. 2x plus 3y minus z equals 15, x minus 3y plus 3z equals negative 4, and 4x minus 3y minus z equals 19. Now, your first reaction might be, wait a minute, that's really overwhelming. But don't worry, we really can solve this system, and it won't take anything tricky or magical. What we want to do is choose pairs of equations from the original system which can be combined to eliminate one of the variables. And once we have eliminated one of those variables twice, we'll be left with a system of 2 equations with 2 unknowns. And you know how to solve that. We've talked about that in the previous 2 lessons. So we'll solve that system, and then we'll basically be done. Not exactly, but we'll just about be done at that point. So let's get started in this example by choosing pairs of equations from the original set. First, I want us to focus our attention on the first and second equations. So let me remind you, those are 2x plus 3y minus z equals 15, and x minus 3y plus 3z equals negative 4. Now, watch what happens when you add those 2 equations together. You're going to get 3x plus 0y plus 2z equals 11. The important thing that just happened is that the variable y was eliminated, and that's exactly what I wanted to have happen. Now, I want to go back to the original set of equations and combine a different pair of those equations with the goal of eliminating the variable y again. I'm going to suggest that we pick the first and the third equations. So here's what I want to do. Why don't you try taking those 2 equations, 2x plus 3y minus z equals 15, and 4x minus 3y minus z equals 19, and try to eliminate the variable y. Okay, that wasn't too hard, was it? Let's check to see what you got to make sure that you eliminated that y correctly. You should have had, when you added, 6x minus 2z equals 34. So notice what we now have. We now have 2 new equations which we built from the original set, both of which are missing the variable y. And they are 3x plus 2z equals 11 and 6x minus 2z equals 34. So we have whittled down, so to speak, the original system into a smaller system of just 2 equations that only has 2 unknowns. And the important thing is that it's the same 2 variables, so the same 2 unknowns in both of those equations. In this case, it's x and z. And now if we add those 2 equations, we will eliminate another variable. We'll eliminate the z. Adding those 2 equations gives us 9x equals 45. And now I can find x. I divide both sides by 9, and I get x equals 5. Now, we know the value of x in the solution. It's x equals 5. We should hold on to that because we don't want to lose that. X equals 5 is part of our final answer. Great. But what do we do now to find the y and the z? Well, the first thing we do is we put the x equals 5 back into either 3x plus 2z equals 11 or the 6x minus 2z equals 34. When we do that, what are we trying to do? We're going to try to find z at that point. And remember, you can put the x equals 5 back into either of those two equations. So I want you to try that now. Plug 5 in for x into either 3x plus 2z equals 11 or 6x minus 2z equals 34 and find z. Okay, I'm going to try plugging the 5 in for x into the first equation to see what I get for z. 3x plus 2z equals 11 becomes 3 times 5 plus 2z equals 11 because x is 5. And that's 15 plus 2z equals 11. Subtracting 15 from both sides gives me 2z equals negative 4. And dividing both sides by 2 gives me z equals negative 2. So now I have a second piece of the puzzle. I now know that x equals 5. I knew that a moment ago. Now I know that z equals negative 2. Am I done? No, I still need to find y, but I'm now 2/3 of the way there. I know x and I know z. What do I do to find the y? Well, I go back to any of the 3 original equations that we started with in this example, and I plug in x equals 5 and z equals negative 2 to find y. Sometimes this idea of plugging these numbers back in one at a time to find some of the other variables is called back substitution. So you might see this phrase back substitution in some textbooks as you're trying to find one variable at a time by plugging in the numbers. So let me suggest that you try going back to, let's say, the first equation in the original set of equations to find the y. Plug in x equals 5 and z equals negative 2 into the equation 2x plus 3y minus z equals 15. And I want you to solve for y. Now, did you get all of those pluses and minuses right? There's a lot of arithmetic here, so let's do this together just to make sure everything worked out correctly. We started with 2x plus 3y minus z equals 15. We're plugging in 5 for x and negative 2 for z, and that gives me 2 times 5 plus 3y minus a negative 2 equals 15. Or 10 plus 3y plus 2, negative times negative 2 is positive 2, equals 15. So I have 10 plus 3y plus 2 equals 15. Adding the 10 and the 2 gives me 3y plus 12 equals 15, or 3y equals 3. And if I now divide both sides by 3, I'll have y equals 1. And guess what? A little at a time, one step at a time, we've just cranked out the solution of this system. It's x equals 5, y equals 1, and z equals negative 2. Now, by the way, did you notice that in this example, I actually found the value of x first, then I found z, and then I came back and found the value of y. The order in which we find the numbers that fit those variables does not matter. You don't have to find the x first, and then the y, and then the z. You can find them in any order. Whatever order is best is the order in which you should try to find those values. Now, before we move to the next example, let's just check to make sure this is really the solution. Let's be honest, there was a lot of arithmetic in what we just did for this one example. So I'm going to suggest we go back to the original 3 equations, plug in the value for x, the value for y, and the value for z, and make sure we really got a solution. So let's do that here. We had, first of all, 2x plus 3y minus z equals 15. Plugging in x equals 5, y equals 1, and z equals negative 2 gives me 2 times 5 plus 3 times 1 minus negative 2 equals 15. And the left-hand side then is 10 plus 3 plus 2 which is 15. So 15 equals 15 is true. That equation is fine. Let's try the second one. X minus 3y plus 3z equals negative 4. Plugging in my information for the solution gives me 5 minus 3 times 1 plus 3 times negative 2 equals negative 4. Or 5 minus 3 minus 6 equals negative 4. And now if I walk through those subtractions from left to right, according to my order of operations, that's going to be the same as 2 minus 6, which is the same as negative 4, and that equals negative 4. So the second equation also checks out. That's good. Let's try the third. 4x minus 3y minus z equals 19. Plugging in x equals 5, y equals 1, and z equals negative 2 gives me 4 times 5 minus 3 times 1 minus a negative 2 on the left-hand side, which is 20 minus 3 plus 2, which is 17 plus 2, which is 19. And that equals 19, which was the right-hand side. And so all three equations were true once I plugged in that information. And that tells me that I had the correct solution, which is fabulous. Now, I'd like to move to a second example, and I'd like to suggest that you try this one yourself. Now, it's going to take some time, and you're going to want to be careful as you deal with all these plus and minus signs, for example. But start the video again whenever you think you have the answers. Here's the system. Let's solve 8x plus 2y minus 4z equals 0, 2x minus 3y plus 3z equals 9, and negative 6x minus 2y plus z equals 0. Well, do you think you got the right answers? Let's check. We need to pick a variable which we can eliminate using two different pairs of equations from the original system of three equations. It doesn't matter which pairs you choose, and it doesn't matter which variable you choose to eliminate first. I'm going to start by picking the first and the third equations in the system, and those were 8x plus 2y minus 4z equals 0 and negative 6x minus 2y plus z equals 0. Now, as with the systems of two equations, I'm allowed to multiply any of my equations by a constant. So I'm going to start by multiplying the equation negative 6x minus 2y plus z equals 0 by 4. And when I do that, I'm going to have the following new pair of equations. 8x plus 2y minus 4z equals 0, which I didn't do anything to, and negative 24x minus 8y plus 4z equals 0. And remember, when you multiply that 0 on the right by a 4, you get 0 back. 4 times 0 is 0. Sometimes students want to write down a 4 there, as if they were doing 4 times 1 instead of 4 times 0. But keep in mind, 4 times 0 equals 0. Now if we add these two new equations that we've built, we will eliminate the variable z. And that's what I was trying to do, was eliminate z. And when I do that, and I make that addition work, I get negative 16x minus 6y equals 0. Now, let's go back to the original system again and see if we can pick another pair of equations with the goal of eliminating z. Since I eliminated z just a moment ago, I need to eliminate z again. It's one of the most important things here, eliminating the same variable twice. This time I'm going to pick the second and the third of the original equations, and I'm going to multiply that third equation by a negative 3. And my new system then, or new subsystem as some people might call it, would be this. 2x minus 3y plus 3z equals 9, and 18x plus 6y minus 3z equals 0. Notice that if I add these two equations together, z will be eliminated again. That was my goal. And when I do that addition, I get 20x plus 3y equals 9. So now I have two new equations that only have two variables in them. Negative 16x minus 6y equals 0, and 20x plus 3y equals 9. Now what do I do? Well, I've just got a system of two equations with two unknowns. We can eliminate another variable now and see if we can come up with the start to finding the numbers in the solution. I'm going to suggest that we eliminate the variable y here if we just play with the equations just a bit. One way to do that is to multiply the second of these new equations by a 2. And when I do that, that's going to give me the following little system or subsystem. Negative 16x minus 6y equals 0, and 40x plus 6y equals 18. Do you see why I multiplied by that? Because now the variable y can be eliminated by just adding those two equations. And when I do that, I'm going to have 24x equals 18. I've eliminated the z, and then I eliminated y step by step, and now I'm just down to x. And if I divide both sides of 24x equals 18 by the number 24, I will isolate the x, get it by itself, and x will equal 18 divided by 24, and after I reduce that a bit, that's the same as 3 over 4, or 3/4. So I now know part of my solution. X equals 3/4. And now what I want to do is back substitute to find the y, the value for y. I can do that by using either of the two equations that had just two unknowns in them that I was just working with a moment ago. I'm going to use the second of those, even though it really doesn't matter which of the two I use. I'm just going to pick the second one of those and plug in x equals 3/4 and see what I get. That equation was 40x plus 6y equals 18. And now I know x is 3/4, so I'm allowed to plug 3/4 in for x. And when I do, I'm going to have 40 times 3/4 plus 6y equals 18. Now 40 times 3/4 could be a little tricky, but that's going to simplify to just 10 times 3, which is 30. So I have 30 plus 6y equals 18. Subtracting that 30 from both sides gives me 6y equals negative 12. 18 minus 30 is negative 12. And dividing both sides by 6 gives me y equals negative 2. So now I have both the value for x and the value for y. I just need the value for z. What do? Well, I go back to one of the original equations that we started the example with. I plug in the value for x, and I plug in the value for y, and all that will be left is solving for z. So let's go back to those original equations. I can pick any of the three that I want. I'm just going to pick 8x plus 2y minus 4z equals 0. Now I'm going to plug in 3/4 for x and negative 2 for y, and then I'm going to solve for z. Let's see what we get. We have 8 times 3/4 plus 2 times negative 2 minus 4z equals 0. 8 times 3/4 is the same as 24 over 4, which is 6. So I'm going to have 6 minus 4 minus 4z equals 0. And 6 minus 4 is just 2. So I have 2 minus 4z equals 0. Now I subtract a 2 from both sides, and that gives me negative 4z equals negative 2. And now if I just divide both sides by negative 4, I will have z equals negative 2 divided by negative 4. The negatives will cancel one another. I'll just have 2 over 4, which is the same as 1/2. So if we haven't done anything wrong in all of this arithmetic we've done, then our solution is x equals 3/4, y equals negative 2, and z equals 1/2. And if you got those answers, congratulations. Now, I'm not going to take the time to check that answer here. I'm going to let you do that on your own. Just plug those values into the original equations to make sure that the equations are true. That's going to be our confirmation that we did everything correctly. But let me say a couple things before we move to the next example. First of all, checking that those numbers really work as a solution is important. So just because we're not doing it together right now doesn't mean I think it's not important. It really is important. So please make sure you do it. And secondly, notice that these problems aren't hard, but they are time consuming. They do take some work. They take a lot of care with your arithmetic. You're going to want to be careful about it and give yourself time. Don't get impatient with them. Just work through them step by step and you'll be fine. Okay, let's look at another angle on these systems now by looking at the following example. Here it is. X plus 2y plus 3z equals 10, negative 2x plus 3y minus 5z equals 30, and 5x plus 10y plus 15z equals 20. Now, how do we start? Well, we start by eliminating one of the variables. We have to sort of eliminate it twice, if you will. We can choose any of the variables to eliminate, but there's really an obvious choice, so to speak. I'm going to suggest that the best one to eliminate would be the x, and that's because the x term in the first equation only has a 1 in front of it. And that basically allows me to multiply that equation by whatever I need so that the elimination will go quickly. So let me show you what I mean. Start by choosing the first two equations, x plus 2y plus 3z equals 10, and negative 2x plus 3y minus 5z equals 30. What would you multiply that first equation by in order to eliminate the x? You're going to multiply it by 2, and then you're going to add. And when you do that, multiplying the whole first equation by 2, remember you have to multiply everything on the left and everything on the right of that equation by the number 2. When you do that, and then you add, the 2x minus 2x will become 0x, and the x will be eliminated, and you'll be left with 7y plus z equals 50. So we've successfully eliminated the x in this one case, and now I have to go back to the original system of equations and pick a new pair that will allow me to eliminate x. Again, you don't want to go eliminating y or z now. You've started down the path of eliminating x. Now you have to do that again. So let's take the first equation. I like it because it has that 1 in front of the x. And the third equation. And that's going to be x plus 2y plus 3z equals 10. And 5x plus 10y plus 15z equals 20. Here's a question. What would you multiply that first equation by to start the process of eliminating the x? Well, you got a couple choices. You could multiply by positive 5 and then subtract, or you could multiply by negative 5 and then add. They're basically the same thing, but I'm going to choose to multiply by the negative 5 and then add the two equations. Now, when you multiply that first equation by negative 5, you must make sure that every term in that equation on both the left-hand side and the right-hand side is multiplied by a negative 5. That's going to give you the following. Negative 5x minus 10y minus 15z equals negative 50. And the third equation, which I haven't done anything with, is 5x plus 10y plus 15z equals 20. So that's my new subsystem, if you will. I want to look at just those two equations. Now my goal was to eliminate the x. Okay, let's see what we get. We add and we get 0x plus, 0y. The y's have also canceled. Well, that's not so bad, but it wasn't my goal, but that's all right. I have 0x plus 0y plus 0z. Actually, everything on the left-hand side has canceled out. And on the right-hand side, I have negative 30. So we haven't done anything wrong, I promise, but now we're down to the equation 0 equals negative 30. Now, it wasn't wrong that we eliminated more than one variable. That's not the problem. But it is wrong that 0 equals negative 30. 0 is never equal to negative 30. And so that's a problem. Is it our problem? No. We just have to interpret what's going on correctly. What does it mean when we come down to something like 0 equals negative 30? Our first response should be that the original system of equations has no solution. And honestly, that's the answer. There's nothing fancier than that. All we have to know is that there simply isn't a solution to the original system, and that's that. Now, let me ask you, we saw systems in previous lessons that didn't have a solution. Do you remember what they're called? They're actually called inconsistent. So the point of this example is that the system I started us with was actually inconsistent. It didn't have any solutions at all. Now, I'd like to close our lesson by looking at one more example of a system with three equations where some of the variables are already missing as you get started. And I just want to make sure we work through this because for some students this can throw them off when they don't see all three variables in all three equations. So let's solve this system. The system's going to be x plus 2y equals 5, x minus 3z equals 7, and y plus z equals 4. Now, you might look at that system and say that it looks really different from the earlier systems we've done in this lesson. But if it really does look different, may I make a suggestion? Why don't you rewrite the system this way? X plus 2y plus 0z equals 5, and x plus 0y minus 3z equals 7, and 0x plus y plus z equals 4. If you insert those extra terms with coefficients of 0, it actually makes the system look a little more familiar. But if you don't mind, you don't need those terms. So I'm going to go back to the way the system looked originally. If you want to keep those terms in, go ahead. It won't hurt. But I'm going to go back to the shorter versions where I don't need those extra terms. Now, one of the beauties of having a system where some of the variables are already missing is that the elimination process is already partly done for us. So we have lots of choices for what variable we want to eliminate in the beginning. So, for example, let's just subtract the first and the second equations to eliminate the x. If you start with x plus 2y equals 5 and x minus 3z equals 7, the first equation minus the second equation is going to give us 2y plus 3z equals negative 2. Now, notice that this equation has a y and it has a z, but it has no x in it. So it's like we've eliminated the x. But notice also that the third equation from the original system, which was y plus z equals 4, was already missing the x. So guess what? We already now have two little equations, both of which are missing x. They only have two unknowns, and they are 2y plus 3z equals negative 2 and y plus z equals 4. So we're already going right down the path that we want to go down. We've already eliminated one of the variables. Now, let's multiply the second of these smaller equations by negative 2. And that will give me 2y plus 3z equals negative 2 and negative 2y minus 2z equals negative 8. Remember, you've got to distribute that minus sign all the way through all the terms. And now if you add those two equations, you just get 1z, or z, equals negative 10. Guess what? We just found z. It's negative 10. Hold on to that. Don't lose that negative 10. And now let's start back substituting to find either the x or the y. In this case, it's going to be easy to find the y first, because we already had an equation like y plus z equals 4, and we know that z is negative 10. So if I plug in negative 10 for z, I'll have y plus negative 10 equals 4, or y minus 10 equals 4, and adding 10 to both sides of that gives me y equals 14. Now you know z and you know y. And if you use those two pieces of information in one of the original equations, you can actually find x. For example, one of the original equations was x plus 2y equals 5. So plug in 14 for y, which you know, and you'll have x plus 2 times 14 equals 5. Now let me pause just for a second. Someone is saying, hey, wait a minute, you didn't use the value of z there at all. But I don't need to. There's no z in the original equation, so we really are fine. And if we start to simplify, we'll have x plus 28 equals 5, which means x equals negative 23. So guess what? Our solution is done. X is negative 23, y is 14, and z equals negative 10. And that's the final answer. Again, you can plug that information into the original set of equations if you'd like to make sure you've done it right. But ultimately, we've actually finished that problem by finding those three values. Now, I'd like to finish today by sharing some thoughts about precalculus, in fact. It turns out that these systems of three equations with three unknowns can be solved by a totally separate method using what are known as 3x3 matrices. A 3x3 matrix is simply a table or an array with 3 rows and 3 columns of numbers. And these matrix techniques, which are often demonstrated in something like a precalculus class, can be extremely useful in solving these kinds of systems. In fact, matrices can be used to solve any system of linear equations, no matter how many equations there are and no matter how many unknowns there are. You could literally have 20 equations with 20 variables and solve such a system with matrices. So if you've enjoyed this lesson on systems of three linear equations, you'll probably really enjoy studying this topic with matrices. As a small bit of advertising, let me tell you that the teaching company has developed a precalculus course, and I know that matrices are discussed there. Next time, I'd like to return to systems involving only two variables or unknowns, but this time we'll look at systems of inequalities instead of equations, things with less than and greater than symbols, to see how these problems are different from what we've been studying for the last few lessons. In this lesson, I'd like to shift gears a bit and talk about solving a new type of system. This time, we're going to talk about systems of linear inequalities. So instead of studying equations like y equals 4x plus 2, we'll be looking at inequalities like y is less than 4x plus 2, or y is greater than or equal to 4x plus 2. Before we begin even talking about these kinds of systems, there are a few questions we need to answer. First of all, what does a solution of an inequality look like? Well, let's go back to the inequality y is less than 4x plus 2. Notice that one solution of this inequality is the point 1, 3, because if we plug in x equals 1 and y equals 3 into that inequality, we're going to have 3 is less than 4 times 1 plus 2, or 3 is less than 6, and that's a true statement. So that would be one solution. But the next question to ask is, what do all of the solutions look like? Or what does the set of all solutions look like? How can we see that? How can we visualize that? Well, the answer is pretty simple. We start by graphing the straight line y equals 4x plus 2. This line is going to serve as a boundary or as a wall, cutting the xy plane into two pieces or two regions. One region which is above and to the left of the line, and the other which is below and to the right of the line. It turns out that all of the solutions of the inequality will be in one of these two regions, or halves of the xy plane, if I may call them that. So the real question is, which half is it? Well, remember that we already showed that 1, 3 is one of the solutions. So where is the point 1, 3 compared to the line that we drew? Well, it's in the region of the plane that is to the right and below the line. And that tells us everything we need to know. The set of solutions to the inequality y is less than 4x plus 2 is the whole part of the xy plane that is to the right of and below the line y equals 4x plus 2. So when we graph this inequality, we actually shade in that whole region and we're done. Now, I need to make one subtle point that's very important about the example we just did, and then we'll move forward. When the inequality is a strict inequality, in other words, when the inequality symbol we're dealing with is strictly less than or strictly greater than, We're actually going to draw the boundary line with dashes to remind us that none of the points that live on the line are actually in the set of solutions. But when the inequality isn't strict, so when we're working with less than or equal to or greater than or equal to, then we're going to draw the boundary line as a solid line. And that's going to remind us that the points on that line really are in the set of solutions. Okay, there's one more issue to think about before we jump into some examples of systems of linear inequalities. What will the solution sets look like if you're looking at the system of linear inequalities? Remember, when we're solving systems of linear equations, we're looking for intersection points, and we'd like to find a unique solution in that process, assuming the system is independent. Well, when we're looking for solutions of systems of linear inequalities, we're still looking for intersections. But now we're often going to be finding the intersection of two regions of the plane, two pieces of the plane, not just the intersection of two straight lines. So the solution sets are going to be big, and the easiest way to see them or to find them is to actually visualize them on the XY plane. So we're going to go back to the method of graphing that we talked about a few lessons ago to actually find these sets of solutions. Okay, now that we've made these sort of opening comments, let's start looking at some very specific examples of solving systems of linear inequalities. The comments I made earlier were really just about one linear inequality. Now I want to consider two linear inequalities at a time, and I want to solve those kinds of systems. So here's an example. Solve this system of linear inequalities. Y is less than or equal to 4, and y also needs to be less than or equal to 2x plus 1. So let me just make a quick comment. In order to solve this system, I want to find all of the points in the xy plane. Those points are going to be x comma y, such that the y's are less than or equal to 4, and the y value has to be less than or equal to 2x plus 1. I need all the points that solve both of those inequalities at the same time. All right, how do we start? Well, we start by drawing, if you will, these boundary lines. So I look at my first inequality, and I see that the boundary line for that is going to be the line y equals 4. Remember that that's just a horizontal line which crosses the y-axis at 4. Okay? I then look back at the inequalities, and I remember that I'm looking at y is less than or equal to 4, and those are going to be the points below the line y equals 4. For example, the point 3 comma 1 is a solution of the inequality y is less than or equal to 4 because 1 is less than or equal to 4. So I know that whatever I shade in needs to include the point 3 comma 1. So I shade in this region, which is below the line y equals 4. Notice also that that inequality, y is less than or equal to 4, is not the same as y is strictly less than 4. What does that mean? Since I'm dealing with y is less than or equal to 4, my boundary line is going to be drawn as a solid line rather than a dashed line. Okay? So I've actually done everything I need to do now with y is less than or equal to 4. I've drawn a solid horizontal line through the y-intercept at 4, and I've shaded all the points below it because all of those points represent the places where y is less than or equal to 4. Now, on this same set of axes, with all this shading already done, I now want to look at the second inequality. It was y is less than or equal to 2x plus 1. The boundary line for that inequality is going to be y equals 2x plus 1. And that line is pretty easy to draw if you think back to some of our earlier lessons. It's the straight line with y-intercept 1 and slope 2. So we ought to be able to draw that pretty well, and that goes pretty quickly. Now, next question, and you should always ask it at this point, Is it a solid line or is it a dashed line? It's very important. Well, this inequality is a less than or equal to inequality. Remember, we're doing y is less than or equal to 2x plus 1. That's not a strict inequality because it includes the equals. And therefore, when I draw this boundary line, I'm also going to draw it as a solid line. So I have two different boundary lines, and in this problem, they're both solid, not dashed, because both of the inequalities included the equal sign. Now, I need to shade in the points which satisfy y is less than or equal to 2x plus 1. I've basically got two choices of shading. I can either choose the points which are below and to the right of the line. And in order to do that, I could check, for example, the origin at 0, 0. If I plug in x equals 0 and y equals 0 into the inequality, then I would have 0 is less than or equal to 0 plus 1, or 0 is less than or equal to 1. Is 0 less than or equal to 1? Yes, it is. So we want to shade in the region that includes the origin 0, 0. And that's the region that is below and to the right of this line. Now, your paper might be getting a little colorful right now. There might be a lot of shading going on, but that's okay. Let's now finish the problem by interpreting what we've done. Once you've shaded in these two separate parts of the xy plane, there was a part below the horizontal line, and now there's another part below and to the right of that other line, you actually see four regions of the plane. There's going to be a region that didn't get any shading at all. There are two regions that have just one shade, if you will, and there's one region which was actually shaded two different times, once for the first inequality and once for the second inequality. That region that has the two different shades is actually the intersection of the two sets of solutions for the individual inequalities. And it's that region, the set of intersection points, which are going to satisfy both of the inequalities at the same time. Guess what? That shaded, if you will, double shaded region, the set of intersection points, is the final answer. So that part of the plane turns out to be the solution set for the system of inequalities. Now, we could check our answer, and we really should check our answer, but how do you do that? Because now we have all of these points in the xy plane which are actually in the set of solutions. Well, let me make this suggestion. Just pick one or 2 points that are in this region that you think is your set of solutions, and choose the x and y values of that point, or a couple points, and plug those in to both of the inequalities in the original system. If you do that pretty quickly with 1 point, it'll at least be a decent check that you're probably on the right track with your solution set. So let's do that here. One of the points in our region that appears to be the solution is 2, 0, which is right on the x-axis. Let's check to make sure that that point really is a solution of the two inequalities. All right, so first we had y is less than or equal to 4. The y-coordinate of the point 2, 0 is the 0. Is 0 less than or equal to 4? Yes, it is. So that point really is in the solution set for that inequality. Now let's try the same point in the other inequality. Y is less than or equal to 2x plus 1. If you let y be 0 and the x value be 2, because I'm looking at the point 2, 0, then I have 0 is less than or equal to 2 times 2 plus 1, or 4 plus 1, which is the same as 5. And you have to ask yourself, is 0 less than or equal to 5? The answer is yes. So we know that that point actually satisfied both of the original equations, or inequalities, I'm sorry, these aren't equations. It satisfied both of the original inequalities. And because of that, we know that that 1 point is in the solution set, and we have confidence then that the region of the xy plane, which was the intersection of the two regions, really is the set of solutions for that system. Okay, I'd like to move to another example, but this time I want you to try to graph it yourself first. Now you need to be careful of a couple things. Remember, first, you need to ask yourself about the direction of the inequality. Are you working with a greater than or a less than? That's very important. And secondly, also keep in mind that you have to worry about whether your boundary lines are solid lines or dashed lines. Remember, if the inequalities are strictly greater than or strictly less than, then the boundary lines need to be drawn with dashes. Okay, here's the system of inequalities I want us to now consider. Solve the following system. Y is greater than x minus 3, and 2x plus y is less than 4. Now, the first thing you need to notice, as I mentioned a few minutes ago, is that both inequalities are strict here. One is a strict greater than, and the other is less than. And that means that both of the boundary lines that you draw are going to be dashed. Okay, so that's the first thing we need to notice. By the way, in some other examples, you might have one of the inequalities which is strict and another inequality which is not strict. You might have, say, less than for one of them and greater than or equal to for the other. That means that one of the boundary lines would be dashed and the other boundary line would be solid. It's perfectly fine to do that. In this case, both of my boundary lines in this example are dashed because both inequalities are strict. All right, now let's start by drawing the first boundary line, and in this case, that's going to be y equals x minus 3. Now the beauty here is that that's already in slope-intercept form, slope of 1 and y-intercept of negative 3. So that's not hard to draw. That's great. Remember to draw it dashed because the inequality was strict. Now, in this case, I want to shade in the points that satisfy y is bigger than x minus 3. So here's a question. Which part of the plane do you think this represents? It's either the part that's sort of above the line and to the left, or the part that's below the line and to the right. So if you're not sure which part it is, let me give you a hint. As soon as you can find one point that's in the right region, then you know that that's the region you have to shade in. That's all you have to do. So I'm going to pick a point, and I'm going to try to do it sort of intelligently to minimize my work. Okay, you might think of it as mathematical laziness. I don't want to think of it that way. I like to think of it as mathematical intelligence. I'm going to pick a point which I can plug into the inequality and quickly check to see if things are true. And I think the best point for that is the origin, where x is 0 and y is 0. So here's what I'm asking now. Is the origin in the solution set of the inequality y is greater than x minus 3? Plug in 0 for x, plug in 0 for y. Let's see what you get. The left-hand side, y, is just 0. The right-hand side becomes 0 minus 3, which is negative 3. So the inequality says 0 is greater than negative 3. Now, you got to pause and ask yourself, is 0 greater than negative 3? Well, the answer is yes. And if that's a bit confusing, by the way, draw a quick number line, plot 0 and plot negative 3, and ask yourself if 0 is to the right of negative 3. And it is. So the answer to whether 0 is greater than negative 3 is yes. And that means that the origin is in the solution set. So I need to shade the part of the plane which is above and to the left of the line. Because do you see that the origin is above and to the left of the line? Good. Now you've done basically half the problem. You started with the first inequality, you drew in its boundary line, in this case dashed, and then you shaded the part that's above and to the left because that's the part that satisfies that inequality. Now, let's move to the second inequality, which is 2x plus y is less than 4. Well, I got to start the same way, draw in the boundary line, which is the line satisfying 2x plus y equals 4. That might not be the easiest thing to draw until I rewrite it in slope-intercept form. But that's not too hard. Just subtract 2x from both sides, and you'll have y equals negative 2x plus 4. And that's in slope-intercept form. Slope of negative 2, y-intercept of 4. And once you know that, you can plot that line pretty quickly, and you'll have your second boundary line. Now, remember, that line has to be dashed. I'm sorry to keep harping on it, but it's an important, albeit subtle, fact that you have to keep in mind. Now, you've drawn that second boundary line. You still need to shade in the region of the plane that's being cut through by that line. In other words, you've drawn the second line at y equals negative 2x plus 4. It has now sliced the plane into two pieces. Which of the two pieces corresponds to the solutions of y is less than negative 2x plus 4? Well, you have the points which are below and to the left of the line, and you have the points which are above and to the right of the line. Which ones do you choose? Well, you pick the ones which are below and to the left of the line. And that's because the y is less than negative 2x plus 4. Remember, if you can tell which region to shade, or if you're having trouble with it, I should say, just pick a point on one side of the line. If that point makes the inequality true, then you shade that side. If that point doesn't make the inequality true, then you shade the other side of the plane. It's actually that simple. So now we shade in this region as well. And what you see, just like in the previous example, is this. Your XY plane now has 4 different pieces. One that has no shading at all, 2 that have just one color of shading, if you want to think of it that way, and then there's a 4th piece that's the overlap where the 2 different colors have now combined. It's that overlapped region which represents the intersection of the 2 individual solution sets. And that intersection is exactly the set of solutions of the system of inequalities that we started with. Every point in that intersection region satisfies the original system of inequalities, and that's the final answer. Okay, let's look at another example now, just to continue practicing, if you will, with these systems of linear equalities and how to solve them. Here's the system. Let's take y is greater than negative x and 3x minus y is greater than or equal to 2. Now, let me start by suggesting that we write both of these inequalities in such a way that the equations for their boundary lines are easy to see. You're going to have to draw the boundary lines eventually. So let's just rewrite these things so that they give us a better hint as to what the boundary lines look like. The first inequality is actually already in such a form because the boundary line for it is just going to be y equals negative x. That's nice. It's a very straightforward line to draw. The other inequality isn't yet that clean looking. So let's just kind of manipulate it a bit to make it look like the boundary line is much easier to see. So that equation was 3x minus y is greater than or equal to 2. I referred to that as an equation. It's not an equation, by the way, it's an inequality. 3x minus y is greater than or equal to 2. If I add, or in this case subtract 3x from both sides, I get negative y is greater than or equal to negative 3x plus 2. Now let me just remind you of something. When you add a negative 3x like that to both sides of an inequality, or if you want to think of it as subtracting 3x, the symbol, the inequality symbol does not change. So I'm now at negative y is greater than or equal to negative 3x plus 2. In order to clean that up just a bit more, I want to multiply by negative 1 or divide by negative 1 so that I just have y on one side. And when I have that, I'll have y is less than or equal to 3x minus 2. When you multiply or divide by a negative number, like negative 1, that's when the inequality symbol must switch. So my inequality now is really a less than or equal to, it's y is less than or equal to 3x minus 2. So I have that inequality, and the other one just comes along, y is greater than negative x. Perfect. Now, I've accomplished something. I can now sort of see the boundary line equations much easier. I've got y equals negative x, and I have y equals 3x minus 2 as the boundary lines. So, what are the steps now? You need to draw those boundary lines. We have to shade in the correct regions, that's important, and then we find our solution set by looking for the intersection of the two shaded regions. Let me suggest that you try that yourself now. Let me remind you what you're doing. You want to solve this system, y is greater than negative x, and y is less than or equal to 3x minus 2. Try it yourself. See how you do. Okay, now let's see. Let's walk through the steps and let's make sure that we got the same answers. That's always fun to do. So the first boundary line is y equals negative x. That's pretty easy to graph. That has the origin as its y-intercept because it's the same as y equals negative x plus 0. And it has a slope of negative 1. So it's going to slice right through the origin with a slope of negative 1. Okay, that's perfect. Remember that this first inequality is a strict inequality, so that boundary line needs to be a dashed line. Now, I want to pick the right region where y is strictly bigger than negative x. Now, unfortunately, the origin, which is my favorite one to pick, is right on the boundary, so I can't choose that. So I need to pick another point somewhere in the plane and check to see if that point is in the solution set for that inequality. Let's pick something like 4, 2. Okay? If you let x be 4 and y be 2, and you plug those into the inequality, you're going to have 2 is greater than negative 4. That's a true statement. So I want to shade in the region which includes the point 4, 2. And that's going to be the region which is above and to the right of the line that I drew. Okay? So that's so far so good. We've got basically half of the problem now done. I've shaded in the part of the plane that's going to satisfy the first inequality. Now, let's try doing the same with the second inequality. I need to start by drawing the boundary line for that inequality, and that's going to be y equals 3x minus 2. And that's going to be a solid line because the inequality that it corresponds to is y is less than or equal to 3x minus 2. And drawing y equals 3x minus 2 isn't too hard. I've got a y-intercept at negative 2, and I have a slope at plus 3. Okay, now I've drawn my line, and I've drawn it as a solid line in this case, and now I need to see which region I should shade. And now my good friend, the origin, is something I can plug in, and I can check to see if the origin is in the solution set for this inequality. So let's try it. I'm going to plug in y equals 0, and I'm going to plug in x equals 0. And when I do that, I'll have 0 is less than or equal to 3 times 0 minus 2. And that's the same as 0 is less than or equal to 0 minus 2, or 0 is less than or equal to negative 2. Now, is that true or false? That's false. And that means that for this inequality, the origin is not in the region I want to shade. And that means I want to shade the region on the other side of that line and avoid the origin in that case. And at that point, I'm back to the same kind of problem I had before. Namely, I've taken my xy plane and I've drawn two boundary lines. I've shaded in the appropriate pieces, and the xy plane is now colored in 4 different ways. There's a part of it that has no shading. There's 2 parts that have 1 color of shading, and there's this 4th part that has the intersection, if you will, the 2 different shadings overlapping one another. And it's that one of the 4 pieces that I want to keep. That one intersection space, if you will, or region, is the solution set for this system of inequalities. Well, today's lesson really brings us to the end of a nice sequence of lessons that we've spent studying systems of equations and inequalities. We've taken a lot of time to discuss how to study these things, the different techniques for studying them. Ultimately, the idea was that we had straight lines that were being drawn in, say, the xy plane, for example, and we wanted to understand how those lines interacted with one another. We were looking for intersection points in the case of systems of two equations with two unknowns. And in today's lesson, we were looking for systems of inequalities. So we were seeing how regions of the plane interact with one another, but we were still just looking for intersections. And that's the key to basically all of these lessons on solving systems. In our next lesson, I'd like to shift gears quite a bit, in fact, and start talking about a very new topic. We're going to leave linear equations and graphs with straight lines behind, and we're going to move on to things called quadratic polynomials. These look a little like lines and their equations because there will be an mx plus b, if you will, hiding inside. But we're also going to add in a term which will have an x squared. So we'll be looking at things like x squared plus 2x plus 1 rather than just 2x plus 1. That's going to change the graphs tremendously, and it's also going to change the mathematics, the algebra that we get to do with these quadratics. I look forward to talking with you then.